Good morning, everyone. We are going to start our workshop now. So, behalf of RBCDSAI, I would like to welcome you all for the second day of 8th RBCDSAI workshop on recent progress in data science and AI.
Sorry.
Today we have 5 faculty affiliated with Robert Bosch Center of Data Science and AI will present their work in different areas of AI and data science. I would like to invite Dr. Mohit for anchoring the workshop. Mohit, would you like to take forward and introduce Dr. Pratyush Kumar, who is the first speaker?
Thank you, sir. Yeah. So once again, on behalf of the RBCDSAI team, I welcome everyone to the second and final day of this workshop. Let me introduce to you our first speaker. Dr. Pratyush Kumar is an assistant professor in the Computer Science and Engineering Department at IIT Madras. Before joining IIT, he spent over 2.5 years at IBM Research at Bangalore. With Dr. Mitesh Kapra, he co-founded 1/4 Labs and AI for Bharat. His research interests include deep learning, real-time scheduling, and cyber physical systems. Over to you, sir.
Thank you, Mohit. Am I audible?
Yes, sir.
Also visible?
Yeah.
Okay. Yeah. Thank you. I have a bit of a challenge at my end, which is that I prepared some slides to show you all, but it's on a website called slides.com, and somehow, at least now I logged into it, it seems not to open. So which means that I have to do this without slides, which is a bit of a pity. I'm just trying to see if we can, if I can get that going.
Pratyush, maybe Ramakrishna can go first, and you may be able to figure within that.
That would be great. I think so. I think half an hour should be a good time to let the cloud recover. Yes. Is that possible?
Would that be okay with you?
Oh yeah, I just need a couple of minutes to set my headphones and all.
Okay. Okay.
Yeah. Thanks for that. I think without
Let me know when you're ready, sir.
So, can you introduce Ramakrishna? Yeah. Thanks.
Professor Ramakrishna Pasumarthy will be taking over the first talk. Professor Pasumarthy is an associate professor at the Dynamics and Control Lab under the Department of Electrical Engineering at IIT Madras. His interests lie in the area of modeling and control of complex physical systems. His research interests include identification and control of cloud computing systems and analysis and control of power, traffic, brain, and cloud networks. He has co-founded IMO Motion Tech, an healthcare company that specializes in assistive and rehabilitation devices for movement disorders.
Okay, I hope my screen is visible and I hope I am audible.
Yes, sir.
Yes, yes.
Perfect. Uh, okay, good. Good morning, everybody. It's a pleasure to be speaking to you all. I will be speaking on functional controllability of brain circuits. This is a collaboration with Stanford University, MS Ramaya in Bangalore. And for the network science concepts and network controllability, I collaborate with Dr. Rachel at IIT Madras and our joint PhD student, Ms. Valli. Okay, so the way I will do this is I will not make it too technically intensive. I'll just give a brief overview of the tools that we use in understanding the brain, so to speak. So first, I am not a neuroscientist or a neurophysicist. So much of my talk will concentrate on how to apply network science concepts and control theory to use these as tools to understand the human brain dynamics better. Okay, and then when I say dynamics, so okay, you're usually over the day go through several moods, and what happens really inside the head is what we would be like interested in, right? Okay, so the tools that we look at is okay. Where there are no first principle models that you cannot write down equations for the brain like you could do for any physical system, which you learn from high school physics and later on in your academic journey. Things would be based on, okay, what can we do with the data that we'll collect? I'll shortly explain you where this data comes from. So once I have data, can I infer some kind of models from the data? Does the data look like a network? How stable is the data? So stability analysis here is important because we have no ground truth to verify if our results are correct. So we just look at robustness of the results over a large number of subjects, and finally look at how control theory can help understanding some of the phenomena that occur. Okay, so a quick crash course in one slide on what are the components of complex network. So you have several subsystems which are called nodes that are interconnected to each other via some edges, and the edges capture how these subsystems talk to each other. And this combination of nodes and edges creates a structure that will decide how the overall system functions. It's like, loosely speaking, if you're an electrical engineer, you can talk of a set of generators talking to each other and constituting a power network via transmission lines, which is also referred to as the grid. Okay, so okay, why is this structure important? If I just take a random network where, say, all nodes are linked to each other via some edges, that study is not interesting because there is no underlying structure or no underlying properties that I could exploit. Whereas if you have a network which is not random, which has some structure, you can identify nodes or systems or subsystems classified according to hubs, which are the parts of systems that are connected to a lot of other parts. For example, the orange, the one in the nodes with the orange color here, and then you have and what would you expect that the nodes are strongly connected is they can have larger influence over the network. Then there are communities which are a bunch of people or nodes or agents that are connected to each other, and they can sometimes perform their tasks independently. And last, there are also called the lonely nodes, which are weakly connected nodes. So we will see how each of them influence the performance of a network. So this is about very crash course of how much we need to know about networks. And therefore, I can ask myself a question: can I have a network interpretation of the brain? But not just human brain, but in general. I mean, a lot of experiments happen on monkeys and pigs and so on. So is the brain a network, and can it be modeled as a network? Well, if you just look at it externally, or what you even remember from your high school biology, just a little organ, just like looks a piece of mass or some flesh or just like a tissue which is put together, as a as what looks here in as how it looks here in the picture. Okay, now just by looking at it, I cannot interpret it as a connection of smaller pieces. Okay, so however, okay, this is the only neuroscience terms I will use. So there are things in the brain called sulci, which appear as peaks, and gyri, which appear as troughs. Okay, what these do is not our forte, but we will see what is the implications of this. So these sulci and gyri, which appear as peaks and troughs, they help us identify different parts that have characterized according to different kinds of neurons and varying density of neurons. Okay, so depending on this type and the density or the distribution of neurons, these can be classified to have individual functions. I'll shortly tell you what those mean. So we can therefore classify them as smaller parts called nodes. And okay, how are these nodes connected? So over the last 10 years or a little less, so people have come up with diffusion imaging techniques where they found out some kind of neuronal axons via those imaging techniques, which essentially serve as the wires connected between two nodes. And these wires define how the information transfer happens between this region. So you essentially look at as something like an electrical circuit, like you have nodes or a power network where you have generators at nodes, and then you have wires which connect these generators, or even as a simple circuit diagram. Okay, so based on this, you can classify some regions. I will not give an exhaustive list, but I'll just tell you how different regions are marked in terms of their own functions. So the most prominent is the Salian network, which helps in communicating, which also decides social behavior, self-awareness, and so on. Then there are subcortical regions, which play a key role in maintaining the nervous system, and so on. Then you have attention networks, which are active during attention tasks. Then you have default mode networks, where you're awake, but you do really nothing, where your mind wanders, you remember the past, you daydream. And we'll revisit this network again, and it'll turn out to be quite an interesting result. Then you have frontoparietal networks, which are involved in cognitive control tasks. Then you have the motor cortex, the visual cortex, audio, and so on. And the list is pretty exhaustive. And okay, how to study these regions really depends on what is our interest. Or is it a particular task, or is it a combination of tasks, and so on. And I will also explain you a couple of those experiments that people do. Okay, so the questions that are useful to answer here are the following. So there have been a lot of papers, a lot of research in identifying the regions which contribute to several processes. But the dynamic circuit mechanisms by which these regions talk to each other or interact with each other are not well understood yet. And I will give you a little interpretation of my own understanding of this towards the end of the talk. Then we can ask ourselves, are these interactions, are they between these regions, are they causal, or are they just like wires connected to each other where current can flow in either direction based on the potential difference? Right, that's what I meant by are they symmetric or are they causal? Are these interactions fixed, like are the set of wires fixed, or the topology changes with time? What happens when you do a certain task, when you learn something, when you learn to drive a car, when you learn to play a guitar, for example, right? And then are these interactions consistent among several subjects, right? So if you just look at two identical electrical networks and their behavior, they are the same all the time, but does it happen in brains? And do these interactions and therefore this cognitive, do the cognitive abilities or the behavior change with respect to a certain task that you do? We will also see a little illustration of this. And for example, does the structure remain same while does the structure remain the same while you sleep, while you watch sport, and why do you all of a sudden feel active after a coffee? Right? That's an interesting question to answer. One analogy, which we will again revisit this, is can we look at these connections as and relate to traffic networks? For example, when I look at the picture on the left, the top left is how the New Delhi was during the Janata curfew. Hardly any vehicles, perhaps they are just the emergency vehicles. Then I look at the picture on the top right, which is the Thanksgiving traffic or the traffic during just before the Thanksgiving weekend in LA, the road called California 405. I kind of use this picture a lot because I was myself stuck in one of those highways about 10 years ago, where it took me an hours to just travel 2 miles. And then, of course, you have things where things depend. The traffic depends on are you which side are you going, right? So are you on the lane that comes down or the one that goes up? And typically, human behavior suggests that the incoming lane is always faster. Okay, so what is the relation with what I'm going to talk is if you do not understand anything of the brain and the way the network functions, we will use this as a simple analogy. Okay, so so far, okay, we know about the regions, and then okay, what does it mean by control? So so network theory and control was the two tools which I proposed to use, and if people have had at least a half a course on control theory, they would know that okay, linear state space system models where X are the states, A is the interconnection matrix, or here it's the adjacency matrix of a graph. B will be the input matrix, and U is the control input. Standard results. Okay, so when is the system controllable? There are a bunch of techniques to verify, starting from the Kalman-Rank condition till the Lyapunov equation, and there's a purpose why I use the Lyapunov equation. Okay, so for practical purposes, I mean, whenever we learn of control in our undergrad or advanced level postgrad courses, we don't really worry about what is the control effort required. We just say, okay, this is the control or the control input will come up as a nice equation. You can just simulate on MATLAB and things work beautifully. Sometimes you implement them on standard benchmark systems in the lab, but we never worry about the quantitative measure of how much is the effort required to control the entire system. For example, how much so if I want to stop the spread of COVID-19 in a week, that would be a lot of effort and a lot of money. It's not that it is not practically impossible to detect and isolate everybody and so on, but these are practically impossible measures to implement, and therefore we let the virus propagate, and in that process few people will die, a lot of them will recover, and so on. But the quantitative measures, when especially dealing with large scale networks, are absolutely necessary. And therefore we use what is called the trace of the Gramian that is inversely related to the control energy. So if I just use this quantity here, which just depends on my A and B matrices, I can give a fair estimate of how much is the control effort required to perform a certain task. Okay, so what we are interested in, therefore in assigning a set of value to each node or a bunch of nodes, which will influence each node or the entire network, which will assess the influence of each node to the entire network, right? So this is more like an actuator placement problem, like as dual to the sensor placement problem. So what are the best set of actuators that I could use? Where can I place those actuators to maximize my control effort? Okay, so now I will not really go into the details of the derivation, but can I just relate everything to the network properties, right? Can I say, okay, I have hubs, I have these lonely nodes, I have communities. So which of these help in controlling the system fairly easily? So I just plot the graph between the weighted absolute degree. For some reason, I can't scroll my mouse, but okay. So what you see is that in the picture on the left is that average controllability on the right side of the left picture is it is strongly correlated with the absolute weighted outage degrees. So we know what are if a bit of the graph terminology will kind of help you recollect the weighted outage. That's the sum of all the kind of output which goes from that node, or those directed arrows which go out. And we see that the only correlation with the picture on the right is that it always depends on the average controllability is only correlated to the weighted out degree, right? And therefore I can say that the nodes which have a larger out degree are the ones which are expected to have larger influence over the network. And the nodes which have larger out degree can be related to what are called as hubs here, right? So that is not surprising, but this is a validation of that, right? So the nodes which are strongly connected or which constitute hubs can exert larger influence over the network. Okay, how do we make use of this? Okay, now the second thing which I will talk about is, well, are these networks static? So if I look at the first equation here, my E matrix is just constant. Whereas you might in a lot of systems look at this as something at the links that vary with time. For example, if I learn how to play a piano or how to cycle, right? So there might be a lot of coordination happening between the visual cortex and the motor cortex, right? They have to really strongly talk to each other to enable learning. But as learning happens, you would have definitely experienced this, is that you don't really need to look down or or breaking. Much of the thing happens autonomously, or you can just read the notes for the piano and just play without really worrying about where the keys are. You can possibly just play with your eyes closed, right? So now this is an important behavior, right? Where initially you would struggle to find the right keys, right? Or you would struggle to find the balance in your bicycle. So you will typically tend to look down on the pedal and try to see if the balance comes from there. But so this actually means that the links evolve over time. Sometimes it helps to see, okay, where you started with and where you ended with, right? How the link structure ended over time. And that is useful because it can kind of classify or quantify based on how fast people learn, on how slow people learn, which brain structures are rigid, which are flexible, and so on. Okay, so this actually, from the graph theory point of view, it means that the edges may not always offer permanent connections. Okay, and then of course the model is derived by a series of snapshots. So in the left picture, you could just see which links are active at which time instances. And then there are results which we derived recently. Okay, so most of the results I present here are very recent. Some of them are as recent as 1 week old, and they are not yet published. So they're in the process of being published. So we use theory of structural controllability to identify what are the best set of combination of nodes to make the system controllable, and we just propose some greedy algorithms and compare them with brute force algorithms. Okay, we'll come back to the topic and check what is useful for us now, right? So we have now the data collected from the brain. Okay, just assume that there is something which comes out in the form of a time series as you do certain tasks. Can we evolve state space models estimating causal interaction among various regions of interest, and hence can we identify what are the graph structures? Once I identify the graph structures, are there causal hubs? So if you really look at this picture, this little graph here, the node in the red is the one which can constitute a hub, and you see how that has okay, intuitively also it is clear that it can from that node can control all the inputs, because there is a path which takes node 1 to node 4, 2, 3, 4, and 5, and the quantification happens in the form of the weight of the outgoing edges. So you have 0.2, you have 0.5, and 0.2, and so on. Okay, so and lastly, okay, so how can we incorporate control techniques to identify which are the best nodes that I can access to control the entire system? Okay, so I'll just explain you a couple of experiments of what we do and what are our findings. We will not try to spend a lot of time giving it a neurophysiological interpretation. We will leave it to doctors or neurophysicists to do that. It's just like when you go to a testing lab, they will give you all the parameters, but at the end they will say, okay, please check with the doctor to corroborate our claim. So we will be at that stage. We'll just give information to neuroscientists. Okay, so the first set of data that comes from is, okay, so much of this is open source data via the Human Connectome project. So we have a time series data of 264 nodes and 1180 sample points of 100 healthy subjects. We classify them into 121 nodes based on regions and location names. I'll briefly explain you what this means. So the regions are what we talked about earlier, right? Which are the default mode network, the visual cortex, and so on. Okay, how do we get the model? We are not interested in a random graph, so we use the method of thresholding proposed in one of the papers, and that's kind of an interesting area also to work. What is a good identification model? How sparse the identification should be? Okay, so we just say, okay, let's assume for our purposes that we identify in such a way that the brain has one connected component. We will not really look at few regions talking to themselves here, few regions somewhere else, and they are actually not talking to each other. And then try to kind of identify which are the set of nodes that contain the entire network. So here we have 13 distinct regions, and within these regions there are some other nodes which have some individual functions. Okay, so the first result says the following, that we have okay, I still cannot find my mouse. Okay, so if you look at the picture on the left, it will tell me, the network names will tell me the regions which can control the entire network. The DC will tell me the degree of each of that clusters, or each of that or the weighted degree of that node that comes from that point. And if you see that the larger the DC, it has more influence over the network, right? And these clusters can control almost all of the subjects. The remaining 4 you could possibly attribute that as outliers, or maybe or there might be some errors in data. And there are also clusters with poor controllability, which are unable to control the network, even partly in some cases. Okay, so and what we observe in the graph here is that higher the DC or the degree relation, the larger probability that you can control the entire network. So this set of clusters can control the entire 96 subjects because they have fairly higher degree distribution. Okay, why did I mark this DMN? So firstly, this is resting state network. You actually are doing nothing. And it turns out that the default mode networks is quite prominent, whereas the salient node is prominent only in one of in one of the subject, or it occurs just once. So what does this mean, right? So if I just loosely relate to the definition of the default mode network, these are like wakeful rest, when you do mind wandering, when you daydream, and things like that, then that's kind of understandable, because while resting, your mind just wanders. Possibly even while meditating, your mind possibly wanders faster than that if you are at the beginning stage of meditating, right? So this is kind of, even if you do not understand too much of network science, you can say that, okay, a default mode network would be the most active while I'm doing nothing. And that's also is corroborated here. And these are consistent with the findings. Okay, now this is not really important, right? So what is important is how do things change when I am subject to certain cognitive tasks? We'll do one. Okay, I just have to play. Sorry. Okay, so just have a look at the picture, and I'll try to explain you what we try to do here. So, so these are called memory tasks, and in general there are n back memory tasks. So during the task, what you see is that one item appears in different positions on the game board during each turn. One back means the subject has to remember the position of the item one turn before. Two back means it has to remember the position 2 turns ago, and 0 back means you just have to tell the position which happens instantaneously, right? And these are okay. This looks simple, but maybe for people with disabilities, they may struggle and they may have to put in a lot of effort and so on. So what we look at, we classify therefore is in such a way that the 0 back data is a low working memory load condition, whereas the 2 back data can be classified as high working memory load conditions. Now we try to just check if these results are consistent with the resting state data, right? Does the default mode network still has the highest controllability, or is it still the most active? Is the controllability same for 0 back and 2 back conditions? So the process goes pretty straightforward. So we have data from 737 subjects. Again, it's from the Human Connectome project. It's an open source data. We take the data, identify multivariate dynamical systems, observe causal inferences, and then look at what control means. Okay, so this is interesting now, is if I look at the network level controllability, the one on the right, is that first is that the network controllability was higher in the 0 back as compared to the 2 back task. So the more cognitive load, the less your brain is flexible, and it also means that the network controllability decreases with working memory load. And the region that has the highest controllability is the salient networks now, but not it's no longer the default mode network. So this is a very small illustration of what changes in how the structure changes with tasks. So one conclusion here is that I just cannot analyze the dynamic behavior just by looking at the wiring diagram. A lot more happens in the wires as things change, as you do different tasks, as you place port, or several other things. This is one set of classification, a very basic result. There is no ground truth to verify, so we just look at robustness of our results along all the 700 subjects and so on, right? And then of course, then you look at what are the active regions within those networks, and that we leave for neuroscientists to infer. Okay, so
excuse me, sir.
Yes, sir.
Since we are running short of time,
yes,
can
yes.
you please wind up?
Yes, I am winding up. This is my second last slide. Yeah. Okay. So how do we interpret this, right? So if I look at the empty roads, I can say, well, these are easy to control. This is like maybe a resting state. You can look at it. If I look at the Thanksgiving traffic, you will say, well, this is an impossible to control traffic problem. I can just do nothing. Just let it evolve by its own, and then maybe the traffic will reduce in the 12 or 14 hours. Now, in the third picture, the control traffic really depends on which direction of the road you are, right? And that's possibly would mean of causal interaction between these nodes. So this is a simple analogy of understanding why is it difficult to control, or why the controllability properties change as the tasks get difficult, or there are more with more working memory load, the controllability gets different. Okay, so where are we in our understanding? So this is my own interpretation. Maybe not many people would agree, but we have all learned about the history of atoms. Okay, we'll not really go to what ancient philosophers talked about the 5 basic elements, but more recently, where Thomson got the atomic, had this pumpkin kind of model, then until we have now the Niels Bohr till the Schrodinger model. So actually Thomson got a Nobel Prize for that. But so I think in the evolution of this theory and our understanding, we are somewhere near the Thomson's model. And why I say this is because there's still a lot of things to understand and learn. I'm sure that as a control theorist, I would really be interested in to check if there are some nonlinearities in the process. Can I classify learning? Who is good at learning, who is bad at learning, and therefore can I maybe do my classroom lessons based on cognitive abilities of people. In particular, we are interested in distinguishing patients with autism, right? So we have a little funding for a center on precision mental health using big data tools. So can we, in some sense, discover or classify patients with autism? Not at the moment, these are just standard task-based. Can we use these database techniques to actually get some better neurobiological models using deep learning frameworks and so on? So these are our future tasks, and I just gave you just a broad overview on what are the kinds of problems that we are doing and what are the things that we are interested. Maybe next time I can possibly present a lot more interesting results. Thanks for your attention.
Hello,
so
sir.
are people allowed to ask questions, or that's all?
Sir, there has been one question posted in the Q&A box. Can you please take a look?
Yeah, let me do that. So it's in the chat window of.
So I can read the question because anyway, when somebody watches the YouTube video later on, it will be difficult. So in slide 8, is the matrix B a network property like A, adjacency matrix, or something else? How is it constructed?
Okay, so B just will define what are the. So if you're an engineer, you can loosely look at it as where are the which are the control nodes, or where the actuators can be placed. So B is a system property which says, okay, I can possibly maybe if I am looking at a speed control, I can control the speed of the motor, right? So maybe I can place an actuator which decides, or maybe okay. So loosely speaking, it's from an engineering perspective, it's like which are the points that are accessible for control? Where are the locations of the actuators?
And in slide 12, I heard you are considering thresholds such that you have one connected component. Does that one connected component guarantee stability and controllability in general?
Okay, a good question. So the point is that there are no standard or no unified framework for these thresholding techniques, and we do not know much about how the interactions happen. So the thresholding could be such that it may therefore the results suggest, right, that so there are some nodes, some networks which just cannot have control over the entire network. So which could be that there might we might lose out on controllability, but we still do not know which are the nodes that are controllable. And here is just a resting state data. Whereas in the second experiment, because we are just working with regions of interest, because we know the tasks, we know which are the active areas during those tasks, and therefore we can safely assume that these nodes are connected in such a way that they have control over each other. So these are just I think it's just an evolving theory, and I think people have used several methods from lasso till thresholding, because partial correlations always don't necessarily work. But these are just hypotheses that we make and just test our the only verification tool that we have is stability analysis by playing around with the data sets. So the answer is kind of yes and no. Like there is still no ground truth. So somebody can challenge this claim, and I would be happy to accept that.
So I think in the interest of time, I'll probably ask one last question. I'll take liberty. And so in all these networks, right, there's a lot of incomplete information, right? Or false negatives, if you would call them. It's just, we know only like a fraction of the real network and so on. So how much of an issue do you think that is, particularly in something such as the brain? Because I work a lot with other kinds of networks, and there we've sort of trying to live with all these inaccuracies and incompleteness. But I am just wondering about here, how important do you think it is, the fact that we have only a fraction of the knowledge?
Oh, absolutely. I think that's the second. So the entire problem we have here is that we do not know the ground truth, right? So, for example, here I just get consistent results for 96 subjects. What about the 4? Technically, all 100 subjects who are healthy, they should give identical results, but they do not. They are also from the same age group. So these are things which we still have to figure out how to deal with. We possibly still haven't reached that stage because of the limited experiments we have and the limited amount of data. So at best, we just do hypothesis testing. And as the theory matures, I think we might stumble upon a lot more issues which we wouldn't have encountered so far. And that's why I said, we are at like the beginning stages of in the history of atom. And I'm sure these things exist, but just that at the moment there are no clear markers to even classify those things.
Great. Thanks a lot, Ramakrishna. And thanks
Yeah.
again for, filling in quickly.
Yeah, I just asked other people to join at 10. So I'm sorry for those whom I couldn't announce the change in schedule immediately. But well, I think that's okay. I guess I can give them another round of talk.
Yeah,
Thanks.
the YouTube video will be there, so they can always get.
Okay, perfect. Thanks a lot.
Thanks.
Thanks for the great talk, sir. Moving on to the next talk. The second talk will be given by Dr. Pratyush Kumar. For those who missed, Dr. Pratyush Kumar is an assistant professor in the Computer Science and Engineering Department at IIT Madras. Before joining IIT, he spent over 2.5 years at IBM Research Bangalore. He co-founded 1/4 Lab and AI for Bharat along with Dr. Mitesh Kapra. His research interests include deep learning, real-time scheduling, and cyber-physical systems. Over to you, sir.
Good morning, everybody. Am I audible, visible?
Yes, audible, visible. Screen sharing is working.
So firstly, apologies for the change in schedule. And thanks to Ramakrishna for filling in. There was some logistics issue at my end, especially those who joined at 10 a.m. to hear Ramakrishna's talk. Apologies to you. I guess the talk will be available on YouTube, so you should be able to look at it. We can send you the link. Okay, so this is a talk about deep neural networks on mobile CPUs, very different in context to the previous talk about the brain, which shows the diversity in this space, right? And the byline here says efficient characterization of runtime. So we'll be interested in seeing how you can take your deep neural networks and run them fast, or at least characterize how long they would take when you run them on your mobile devices. So this is joint work with Vinod and Surya, who are students at IIT Madras. Surya is headed to Purdue, which is where Anand is a professor, and Sanchari is one of the students with Anand. So it's a joint work between the two departments. All right, so the key ideas I would like to leave you with are 3 important ideas. One is to drive home the message that DL, or deep learning, is not just about these large models, right? So I would like to talk about SysML, which is the keyword that some academicians have set up, which for the last 3 years or so has been seeing quite some work. So I would like to define that keyword for you and leave you with some thoughts about expanding the way you think about research in deep learning. Then the second point would be to zoom into the topic of interest, which is modeling latency or runtime on mobile phones. And during the talk, I would try to give you open questions that we have in this domain, because it's still a fairly new domain. And perhaps towards the end, I can take some questions as well on things you're currently working on. All right, so let's get started. As I said, I want to challenge the way you think about deep learning. Most of us would, maybe those who are working in natural language processing, you might have used a model like BERT. In fact, over the last 1.5 to 2 years, these transformer-based models have completely changed the way we think about natural language processing. Just the same way as maybe the 5 years before that, models like YOLO, based on convolutional neural networks, changed the domain of computer vision. And maybe if you're working in speech, you might be using DeepMind's WaveNet. So all of these are very large models. And when we are typically working with deep learning, we are figuring out how to design these models, how to maybe make changes to them, and how to train them better, and so on. But there is much more to deep learning beyond this cloud of models, right? And that is because you eventually have to execute these models on some hardware, right? Some hardware that you buy, and you'll have to run these models both for training and doing the inference on these hardware devices. But that's not a shortcut, right? There are many other components that come between the model and the hardware. For example, there are frameworks. Frameworks like TensorFlow or PyTorch or Keras that many of you might have used. These are ways in which you express your intent for what the model should do. So they have different domain-specific languages by which you can represent deep neural networks. After you do represent them, you need some kind of a compiler that translates your intended model into instructions which can be further optimized for the hardware. And interestingly, because we are still fairly new into the DL age, we have many options. So there are options from different companies. Some of them are open source like XLA and TVM. But this diversity shows that we are still fairly early in terms of systematizing the way we write programs for deep learning. After this, there is typically something like a runtime or a library that actually takes the compiled code and manages its execution on the hardware. And even here, there are many options, especially demonstrating the variety of the hardware vendors we have. For example, TensorRT from NVIDIA. There are things from Intel, from Apple, Google, and ONNX is a open source tool that is supported by Microsoft. And then even in hardware, we have lots of options. Those of you who have followed this, you would find that today most semiconductor companies are building chips for deep learning. But even more, the software companies like Google, this is a chip from Google, this is the TPU V2, Tesla, which is, I don't know, maybe a car company, maybe a software company, maybe a hardware company, it's not clear. And then there are specialized startups like this one. This is a chip from a company that tries to build what is called wafer scale computing. The chip is actually this big, so it's this big. And it's completely a different way of thinking about semiconductor chips altogether. And of course, there's NVIDIA, though it's the last picture here. Perhaps they are the ones who have benefited the most, at least commercially, in terms of leading the charge on hardware. So what this picture shows with all these icons is that the journey from the models that you build to the hardware where you want to run is actually going through several components, and each of these components are having many options which different designers are designing. For example, the developer of PyTorch, which is open source framework from Facebook, doesn't really directly talk with somebody building a chip here, or even to some extent Intel MKL, which is trying to optimize deep neural networks on CPUs, right? So I think what this means is there are lots of knobs available in this entire stack, which we can continue to tweak to ensure that our models run much faster on the hardware. And that is what I wanted to expose. The first question, therefore, is how do we optimize each of these components so as to maximize performance? Well, why do we want to maximize performance? We all know this. We have models which are going into billions of parameters. Training them takes GPU years. Even running inference sometimes takes multiple minutes at times. So we would want to definitely get more and more performance for these larger and larger models. So how do we take each of these components? How do we optimize the frameworks, the compilers, the runtime, the hardware for deep learning? Interestingly, I think we are in a good inflection point in the history of computing, wherein different domains like NLP, audio processing, computer vision, they all map to compute structures that look very similar. And because of this similarity, I can ask the question, how do I optimize each of these components for deep learning? And that leads to benefits across different domains, right? So that's the first question. And if you think of it, it is really improving systems for ML or DL. So how do you improve the systems that we have for ML? So by the way, compilers is a traditional topic. We teach undergraduate course in compilers, which is a core course. So the question then becomes, how do we improve the techniques in compilers for machine learning? Well, there is also a flip question. So if you ask about what these boxes are actually doing, so each of these boxes involve making lots of automated decisions during design and or operation. For example, A framework is trying to make all kinds of decisions on how to represent and fuse operations. Do I represent something for a convolutional neural network, or as it's typically done now, do I model something which has convolution plus some activation followed by batch normalization? So for those of you who have worked in deep learning, you know that these three operations usually come back to back, and it helps to represent them together. On the compiler front, you can ask questions like, how do you optimize loops? Loops can be unrolled or kept as it is, and these lead to different performances in different devices. They can be tiled and so on. So the question, again, this is a decision to be made by the compiler. For a given program, how do I optimize the loops? Even further on runtime and library, we might be asking questions like, okay, I have these 5 things to do on the runtime. How do I allocate these work items to the different components in my hardware? So again, decisions to be made in the runtime, which are usually to be optimized for performance. And finally, on the hardware, you may ask questions like, how do you place and route transistors? So remember that hardware is being designed, not just being operated. So in the design time, you want to be placing these billions of transistors on the chip. And for decades now, we have had companies that have built algorithms for such placement. But you may ask the question, these are really optimization problems that a designer must solve. So across all these components, we are actually solving optimization problems. And you should be trying to make now the connection to the next thing that I would say, which is that we can use machine learning for all these decisions. Why use standard algorithms, maybe a search using simulated annealing as would be done in the case of hardware? Why not use machine learning? So that is the other side to this question, which is question 2. How do we optimize these components using machine learning? Even if I were executing something standard, maybe let's say I'm doing some database processing, I would still have to compile it, still have to have a runtime and actually execute it on hardware. How can I optimize the performance of database by using machine learning throughout all these components? Okay, so that is question 2. You may think of it as improving systems with ML. So I think when we say SysML, I wanted to define this term for you. We mean both these things. How do you optimize the system stack, which is fairly long, for the deep learning workload, which is a dominant workload today? That's question 1. And question 2 is, how do you optimize each of these components using the new ideas from machine learning and deep learning? And lots of progress is being made on both these fronts, and both of them are very active areas of research. For example, at IIT Madras, we are doing several things on hardware. In a couple of months, we'll be releasing an open source hardware that accelerates deep learning workload. We're also working on how to optimize some of these design automation algorithms. In particular, one question of interest for a hardware designer is, after I have designed the system, how do I know it's actually correct? How do I verify its correctness? And we are trying to use machine learning techniques to verify hardware. On the compiler side as well, we are trying to build compilers which lead to more efficient mapping, especially of loops, onto what are called spatial architectures. I just want to put out these research problems so you know where the focus really is. So we are trying to ourselves work on different problems. But if you see the keyword of SysML, you would find a workshop being held every year on SysML, where all these topics would be explained in great detail. And the good thing also you'd find is that this is an area that is being driven equally by academics and the industry. So you'd find lots of work which are actually working at the industrial scale. So companies like Facebook, Google are actually promoting research and development in these areas. Right. So with that, I hope I gave you an idea of what SysML is. And I think this particular talk is a representation of this bipartite relationship between ML and systems that we have. One important implication this has for students and researchers is that we should be taking a full stack approach. Now, what does that mean? A decade back, you would be fine if you said, I am a hardware engineer. Or somebody else might say, I actually do some AI software. But in today's time, I think it makes a lot of sense for researchers and also students, many of you listening in might be students, to actually think of having a full stack, at least thought process. You might not specialize on the entire stack, but understand what a compiler really does, understand what the operating system is doing when it's trying to run some of these libraries efficiently. What exactly is happening on hardware? So what do we mean by Google is releasing their own chips? I think some understanding of these things would take you a long way. So it's, I think, the time for being just someone who specializes on one component is perhaps over, because the efficiencies that we have in tweaking all these knobs together is so much more. So as I said, this particular talk is an illustration of this two-sided relation. All right, so with that preamble, let me get into the topic of this particular work, which we did with Vinod Surya and also collaborators from Purdue. The motivation is the following, right? So we have lots of neural networks that are shown by these colored bubbles here. On the x-axis, you have operations, which means this is gigaflops, giga floating point operations per second. The more to the right you are, the larger is the compute requirement of that model. And on the y-axis, you have the top one accuracy on a famous data set called ImageNet, which tells you the higher you are, the more accurate your model is for this particular data set. And as you can see, there is a huge spread of models all over the place. And this, in fact, the size of the bubble tells you how many parameters it has. So as you can see here, there's a gradation going all the way to 150 million parameters. So there's a huge gradation of number of operations required, the weights or the memory required, and the accuracy. So I want to take all these diverse set of neural networks and run them on a diverse set of hardwares. As I already told you, there are many different competing methods for designing hardware accelerators or even mobile devices for deep learning. So the natural question is, if I want to map one of these networks that I have designed on one of these hardwares, how do I go about characterizing the latency of my model? In particular, if I say, this is an ImageNet task, which takes an image as an input and tries to classify what is in the image. So if I ask the question, let me take maybe MobileNet v2 and run it on TPU version 2, what is the amount of time required to classify one particular image? So that is the question of latency. Why is this important? Well, it's important for various reasons. On the mobile phone, it would be important because that's the user experience. You don't want to be taking a photograph and then waiting for a long time for the photograph to be processed. On the cloud also, it's important. When you say, hey Siri on your Apple device, it's sometimes actually going all the way to the cloud and doing some processing, and the latency here should be very, very small. So latency is of utmost importance, whether you're on the cloud or on the edge. So the important thing to realize here is we are having this curse of dimensionality in some sense. We have to work with a product space that is the product of all possible networks with all possible devices. So we have a very large space on which we want to characterize latency. Okay, so how do we do it? Well, you can say, let me take a machine learning approach. Remember that we are answering this question with the two frameworks which we had, which is how do we optimize systems for ML and ML for systems. So the question we posed here was a question about how do we do systems for ML? How do we characterize latency for these networks? But let me take the other angle. So the question is, can we learn a model that can predict the latency of a network on a device? Okay. So instead of trying to use standard methods of actually running benchmarks and then doing some kind of extrapolation to other workloads, I can try to learn a model that, given a network, tries to predict the latency on a given device. So here is what that will look like in an image. So you have some network. In fact, this is one of the MobileNet family, as a part of it. So this contains many, many layers like convolution, a bottleneck layer, and so on, for those who are familiar with neural network. And this needs to be run on some hardware. Let's say I choose a particular hardware. I want to characterize on that hardware. I can run it n times, and then I can compute the latency. Okay, so it took on average 3.5 milliseconds. After doing this, I can then represent my deep neural network. So that's actually not hard to do. I can take each layer. I can find out what kind of layer it is, maybe convolutional layer. So I can take a vector that represents what type of layer it is, what the parameters are, for example, the kernel size, maybe there's a stride involved, and so on. So all of that, which you typically encode in a PyTorch or a TensorFlow program, can be vectorized and be used as a canonical representation. Once you have this representation, I can learn a model which takes this representation as input and tries to output this latency, right? And this is the typical supervised machine learning problem. It's a regression problem. Given an input, I would like to go and predict a real valued latency. And if you take many such examples of networks, run them on your hardware, you can train this kind of a model. And once you have done that, the advantage is it will hopefully generalize to unseen networks. So you might put in a new network that comes in the paper let's say in 2021, and hopefully it would give you a latency estimate which is still correct without actually having to execute it on that particular device. Right? Now that's an attractive thing, but the problem is it still works for a single device, right? Whatever device that you chose here, you still have this model only applies to that. So a natural question then is, how do we generalize this to multiple devices? So I would like to have one model that takes a particular neural network and a given device, and for this combination tries to estimate the latency. That would be really good, because if you could do that, even across all the phones that Samsung has, and they keep releasing tens of phones every year, they should be quickly able to characterize the latency of a new model. Okay, so how do we go about doing that? Of course, the key question is we need a representation of the device and use a joint model that takes the existing DNN representation, but somehow represents also my device and then puts it to a model and learns the latency. So the natural question is, what is this representation for the device? So this is a missing blank that we can fill here. If you think about this problem, one intuitive idea that you may have is, let me use the question is really, how do we represent the device? Let me use the properties of the hardware. So when you buy a phone, what does a company try to sell you? It tells you how many cores it has, what is the frequency, what is the DRAM, what's the memory size that you have, and so on. So let's take these headline features and let's try to see if that works, right? So the first thing that we could do, okay, I think that the slides have been reordered. Okay, let me just mention this slightly differently. So the one question, as I said, was to try and represent the hardware. Okay, so you would like to have some representation for the hardware. The other problem that we have, which is question B here, which is how do we collect a large and representative data set to evaluate? Remember that if you're training a model and you want to claim that you have a model that generalizes across networks and devices, you should have a good data set on which you can make this claim. So we need also question B to be answered. And remember, we want to do this in a way that sounds practical. There are lots of devices out there, so we should be able to answer question B and convince people that this works in practice. So that is the first problem that we attack. Though we have a more theoretical question about A, which is what is the representation, the practical question often dominates what we end up doing in deep learning. So in this case as well, question B was the first one that we wanted to answer, which is how do we collect data? So for this, we had to write an application altogether by ourselves. What did this application do? Well, it took several hand-tuned networks which have been proposed in the previous years. For example, MobileNet V1, V2, SqueezeNet. All of these are models that people designed with some clever intuition and have shown good performance. There are also what are called networks generated by machines. So there are neural architecture search algorithms which try to search for good networks. And there have been many over the years: MNAS-net, Proxyless-NAS, Efficient-net. In fact, if you were to ask me, this is perhaps the one direction of most important focus in SysML now, which is how do you automate the process of generating networks? How do you learn the process, the network that learns? So it's actually a meta-learning question. So we took both these things. We took networks that were hand-tuned. There were networks that were generated with AutoML approaches. And we also created many networks of our own. So we had a random neural network generator which can combine these different operators that you see here very efficiently. And the net result was we had a large set of networks that we generated. Then we had to make them somehow work on mobile phones. And there are some techniques that we applied there. In particular, we ran it through something called TensorFlow Lite. We had to quantize it and so on. And then we passed it on to an Android app, which was then executed on many applications, on many devices. The net result was we collected a database of latency for a hardware network pair. And this size of this data set was about 118 networks on 105 mobile devices. So on 105 different mobile devices, we collected the data of running 118 networks, which were a combination of hand-tuned, machine-generated, and also completely randomly generated networks. So that is the first step. I would like to stress on this, right? Though you might have an interesting theoretical idea in SysML, often you need to back it up with good systems design which collect real-world data. Okay, so visualizing the data, once you have the data, the next question to ask, is this actually a good data? Is it data that is, as I said here, is it representative enough to make claims about? So we did a few experiments to visualize it. So one is we were trying to plot here, each dot is one network, and on this x-axis you have the flops or the compute required for inference. And as you can see, this is a cumulative distribution. As you can see, we have a huge spread of networks in this range from, let's say, about 50 to about 400 flops. And there are a few which are even larger than that as well. So a good spread of networks. It's not something that is maybe aggregated in a small region here. There's a reasonable spread. Secondly, we had a large spread of devices as well. Though I said 118 or 105 different mobile devices, we should also probably look at what are the CPUs on these devices. And as you can see here, this x-axis shows different CPUs, and the y-axis the histogram count of how many phones had these CPUs. So there's a reasonable spread of these CPUs as well. So that's the first thing. The second thing that we did to again convince ourselves that this is representative data is actually plot what are called violin plots. So for those of you who are not familiar with this, this is a very interesting way of plotting the spread in data that you have. So for example, this first set of plots corresponds to fast devices which had a mean latency of less than 50 milliseconds across all networks. So on the x-axis, you have mobile devices, and each of these violins, so to speak, represents one device. But what is this little shading here? This tells you the distribution of latencies of the 118 networks on that mobile device. So for each mobile device, we have a little shape that tells you maybe if you take this number here, this is less than 10. So it runs at less than 10 milliseconds, going all the way to something here, which is maybe, I would say, 80 or so milliseconds. So this shows the spread of all the latencies on this particular device, right? And what we have done is we have divided these plots into three categories. The top one is for the fast devices. The bottom one, the middle one is for the medium devices with a latency of 115. And the bottom one is for slow devices with a mean latency of 235. Again, the intention is to convince ourselves that we have actually chosen networks and devices with large variability. The variability in devices is clear given this average latency. On the networks also, it's clear because you have long violins as opposed to short violins. Okay, so now that we have answered question B somewhat convincingly, we can move on to question A, which is how do you represent a device such that this representation is discriminative of its performance on DNNs? Now for this, the first thing that you might propose, if you're asked about it, is I would choose simple features that are used by companies to sell me these devices, right? So I would use things like the clock frequency, the DRAM capacity, and so on. And then see if these headline features are capable of predicting latency on these neural networks. Now we did that. We took these features, like for example, the clock frequency and also in this case, yeah, so I think the left one, let's start with the left one. It's the frequency of the processor, and on the y-axis you have the latency. As you can see, the dots are all over the place. In fact, the little inset here shows the RAM capacity. So the colors of these bubbles denote the RAM. As you can see here, though there is an increasing frequency that somewhat shows a trend of decreasing latency, the trend is not strong enough. Neither is the trend strong enough with respect to the RAM. Sometimes you might have devices with larger RAM, but maybe, for example, this darker point is to the left here of a lighter point here, right? Which has a lower latency, but higher RAM, right? So what we did also was to plot this in this X versus Y plot of actual latency versus predicted latency. So each dot here represents one network running on one device. And if you try to train a model, a machine learning model that takes its features, the clock frequency and the DRAM capacity, we are unable to predict the actual latency, or these points are far away from the Y equal to X line that you see here in black. So the capacity of frequency and DRAM capacity to be good features to predict latency was not shown, right? So we were not able to show that. So how am I doing on time? How much more time do I have, Mohit?
Sir, actually 25 minutes are over, sir. So if you can, okay. Can you please?
All right, yeah. So I'll probably just then go a bit faster, and you can of course ask questions on the ones where you had doubts. Okay, that's what we realized. So I think the result here is that simple features don't work. So this is where the key insight of this paper was, which is let us not go back to looking inside the device to find its features, but instead use a typical machine learning technique, which is that I'm going to fingerprint a device by the latency on a set of deep neural networks. So if you want a model of, let's say, a Samsung phone, don't look inside the Samsung phone to see what processor it has, how much DRAM it has, and so on. Instead, simply run a set of signature deep neural networks on that device and compute latency. So I would here have maybe a set of, let's say, 15 odd networks. And on each of these networks, I run my, on the same device, I run these 15 networks and I compute latencies. And now these latencies will be then used to represent that particular device. So the key insight is, if you want to represent hardware, don't go into the hardware features. Instead, choose a signature set of deep neural networks, run those networks on the device, compute their latencies. You might have to run it a few times to get statistical significance. But once you do that, these latency numbers then represent the hardware. Why? Because somehow we are finding out on what kinds of networks is this device fast or slow, right? So if I have a reasonable variety in the networks that I have chosen here, then these numbers tell me quite a lot about this particular hardware, right? So that was the idea. Of course, the follow-up question then is, how do we choose the signature set? Here we had a few things. I'm going to skip this part. We went back to information theory to see what kinds of networks should be chosen in a set, especially if we don't want similar deep neural networks in the signature set. So there is some choice around that. And then we did a few experiments to see how this works, right? So, the key message is, whenever you're stuck in machine learning with the problem of representation, which is perhaps the most important problem in machine learning, you must think of simply executing things or running things and trying to use the numbers that you get as a way to represent the hardware. A good example in this case is also natural language processing, where you try to represent words, though you might not know the semantic meaning of each word intrinsically. By looking at how words occur in relation to each other, you might try to characterize this word. So that was the inspiration for doing this. We set up experiments to evaluate this. In particular, we use the XGBoost as the model for learning the latency. In fact, I would recommend all of you to be thinking about XGBoost when you want to learn a small model, not something which requires deep convolutional neural networks. It works very well in practice. And we use the R-square metric to characterize how things are. We, of course, did a train and test split of 70-30 percentages. So we did the test on devices completely unseen by this particular model. That's the usual approach. And we only use training set to compute the signature set, right? So remember that we need to find a signature set of neural networks. But even this decision of which networks go into the signature set were done only with the training set of devices. So I will not go into the details given the lack of time, but what I would maybe just stress on this first one, the plots correspond to the different methods in which we choose the signature set. Just look at the one on the left here. This is for the random sampling. This is again y = x-plot, where you have the actual latency on the x-axis, which is the real number that we measured, and predicted latency by the model that we proposed. And you can see that it's fairly closer to this y = x line, much better than what I showed earlier with the simple features. So we are doing fine. So the R-square value is 0.9125, which is much better than reported results in this domain. And it gets better if we do a more clever selection of the signature set. A bit of one comment about the random sampling. It seems like random sampling, which is to choose my signature networks randomly, seems to do fairly well. It's not much worse than the other two. So we just wanted to investigate that a bit more. And what we found was that indeed, if you, on average, random does quite well, and it compares reasonably with the other methods. But there can be times when it does much worse. So on average, it is fine, but you might end up with a bad choice at times. So I think it makes sense to be choosing your networks carefully. The other question also was about the size of the signature net. I would skip this, and I would just maybe make a comment that even as small as 5 to 10 networks are sufficient to fingerprint a particular device. I'll share these slides in case you want to go over this. I would like to spend a couple of minutes on the last point that I want to make, which is the so what part of this talk, right? So how do you use this? So a simple way to use this is, of course, if you're an Android developer and you want to push a new model to the App Store, or the Play Store, and you want to quickly check the latency of this new model on the top 50 Android devices. Then you can do this. You can maintain a model that is across all these devices, and then you can pass it through this model and check the latencies. In fact, this can be a good service that somebody can offer to Android developers. But that is only part of the story. The question is, can we do more? And we thought about this because there's a lot of focus on distributed learning and distributed benchmarking in the machine learning domain. So we wanted to propose this as a way of doing collaborative benchmarking. What does that mean? So let's say you are one particular Android developer, you have some number of devices and you have a particular network, and you did what I showed till now, which you trained a model. Maybe you generalized it across all the models and devices which you had, but somehow the model is not good enough because you don't have access to many devices or you don't have access to many networks. And maybe in this case, just to show this point starkly, you have a predicted value of 70, whereas the actual value is 25, meaning your model is not very good. So what you may do instead of this is to do some learning where other people contribute data. So just like you have some data, maybe there is another developer who has a few devices and few networks and contribute some numbers on this latency. And maybe there are others as well who all contribute some pairs of device and latency numbers. And you put that all to improve your model and improve your accuracy, let's say, get to highly accurate, in this case, exactly same as the actual value. Now, the question is, this seems like a nice idea to propose because different people have access to different networks and different people have access perhaps to different devices as well. So this seems reasonable, but does it work in practice? And we tried to test this out, and I would like to just show you the results of that, maybe, and stop there. What we found, as you can see in this plot on left, there are, on the x-axis, you have the number of devices. On the y-axis, you have a quality of goodness. The higher the value, the better it is. And you have different lines being plotted corresponding to the percentage of contribution made by each person, right? So what you find here is that even if each of these Android developers is contributing only 10% of the numbers, as the number of devices increase, you get very accurate models very quickly. So if you collaborate, the point is, even with a small amount of contribution from each, you can get to very high accuracy reasonably quickly. And just to give you a very concrete example of this, here we have a plot where the number of data points, which is the number of latency, device points that you have, and the y-axis is again the quality of the model that you have trained, and the quality keeps improving as you get more data points. But the point is this: you have 11x improvement in the accuracy as you go from something like 10 devices to 10 data points to 110 data points, and getting 110 data points from, let us say, 5 or 6 different Android developers should not be a difficult task. So the model is highly sensitive to the amount of data available, and even with small contributions from each of these Android developers, we would be able to get to high accuracy. So this makes the case for having somehow a central repository of all this data where we all push our numbers. Remember, I don't have to give out my network. I don't have to share my precious neural network. I only need to share some of its parameters which are enough to compute for the model to work. And that should be sufficient to do this in a collaborative manner. So with that, I will stop. Apologies for taking a bit longer. I'll stop with this summary slide and see if there are some questions. Thank you.
Thanks for the great talk, sir. We have one question from the participants. Mr. Rajiv asks if same hardware with different software versions give huge latency differences. The only change is software optimization. Are you considering the software versions in your model?
That's a very good question. So in fact, if I were to rephrase that question, he's asking, let's say if I use maybe Android version 10 versus Android version 11, my performance might change. So am I considering the software stack as well in characterizing the latency? We tried doing that. So when I talked a bit about the simple features were hardware features, but we also considered adding the software features, but that did not yield good results. So let me just go back to that. So this particular diagram was showing that you can't learn a very accurate model with the headline hardware features, but doing the same with software pitches also did not work. So what we then took is a machine learning approach. We simply execute something on that device and its own software stack and use that to predict characteristics of that device and software. You're right, I should be always saying that it is characteristics of the device, comma, its software stack. So if the same phone is updated later with the next version of Android, you should perhaps rerun the fingerprinting on the signature set and see how that performs. I hope that answers the question.
So we have another question.
Yes.
Can recommendations to improve latency be suggested through this approach?
Good question. We have started thinking in this direction. I just to again rephrase the question. You're saying I have a model which can take latency, which can take a deep neural network and a hardware and gives out a latency. Can you ask questions like, what should I change in my model so that I get a smaller latency? And people are using that. In particular, if you looked at this area of neural architecture search, NAS, people do use models there. So for example, if I have a neural network, which is using a 5x5 kernel for convolution, if I move to 3x3 kernel, how much of an improvement in performance would that yield? If you had a model like what we are suggesting, that would definitely be useful for that question. And that can be then used to search different networks, right? You might say, okay, let me use 3x3 because that's huge for this particular device, and then make some other choices to improve the accuracy. In fact, just one comment on that. What we have found in some other recent work is that some of these networks might work very well, let's say on GPUs, but might work much worse on TPUs. And these kinds of discontinuities are very clear in these models. So I think there is a lot to be done in this space, and I think you should be thinking more about it. Yes, thank you.
Thank you, sir.
Thank you very much. Again, apologies for the longer time. So thank you.
No problem. Moving on to the next talk. The third talk will be given by Dr. Arun Rajkumar. Dr. Rajkumar is an assistant professor at the Computer Science and Engineering Department at IIT Madras. Prior to joining IIT Madras, he was a research scientist at Xerox Research Center at Bangalore. His research interests include machine learning, statistical learning theory, and ranking. Over to you, sir, for the talk.
Thank you. Can you stop?
Yeah.
Is everyone able to see my screen and look at me and also hear me?
Yes, sir.
Okay, thank you. Okay, good morning, everyone. So this is the talk about online learning with applications ranging from, scheduling trucks to nabbing criminals. So let me start with a very high-level overview of what machine learning is. Of course, everyone here knows what machine learning is, unless you are living inside a cave. So what is machine learning? So basically, you are given some data, and then you run it through an algorithm, which is the data-driven algorithm, and out comes a model. And this model can be used for prediction for future data points. So this is like a one-slide summary of what machine learning is. But what is online learning now? Online learning is like machine learning, except that you have one extra component, which is the feedback component. What do I mean by that? So here, the data is not available as a batch, but then you get data one point at a time, and your algorithm processes this data along with the historical data that it has seen so far. And then it makes a prediction for this particular data point that it has seen, right? So you only get the features for the data point, and you need to make a prediction for the, let's say, the class of this data point. Think of it as like an online email spam detection software, where every time an email comes, that is your data point, and then the algorithm has to decide whether this is a spam email or a not spam email. And once the algorithm makes this decision, it gets a feedback from the user, let's say, whether the email was indeed a spam or not. And now it has to take this feedback into its algorithm and then modify its algorithm so that tomorrow, if a different email comes, it has to make a prediction again as to whether it is spam or not, and so on, right? So this is the continuous process that keeps going on. And this is what we mean by online learning, right? So to give some more details, so I think of online learning as having three different paradigms, so to say. The first one is what we'll call as full feedback, which is traditionally called as online learning. The second one is partial feedback with a single state. And the third one is partial feedback with multiple states. So let me explain these three things with three different examples. In the first case, let's say you are trying to predict the value of a stock, whether you need to invest in a stock or not, and you have a bunch of experts who are trying to help you make this decision. Let's say there are 100 experts who give their advice as to whether to invest or not invest. And based on their advice, you kind of go ahead and either invest or not invest in stock, right? So, and once you make this decision, then you get a feedback saying whether the stock really went up or went down, right? So in this case, you can think of your experts as some kind of actions, and then you pick one of these actions, which means you are going with the advice of one of these experts, so to say. And once the feedback is given, it is a full feedback in the sense that you know whether each of these experts was right or wrong, right? So that's what I mean by full feedback, in the sense that you know the answer for each of these actions, right? So the feedback is for each of these actions. On the other hand, if you look at a case such as, let's say, example in healthcare, where a patient comes and you are a doctor, and now you have options as to, you look at the symptoms of this patient, and then you can kind of choose one of the 5 different treatments. Again, there are 5 different actions to choose from. And now you choose one of these actions, which means you give one of these treatments to the patient. And what you get as a feedback is whether the treatment worked or not. But this is feedback only for the single action that you actually took, only for the single treatment that was given to the patient. And it has nothing to do with the other treatments which you could have given, but you did not choose to give, right? So this is what we'll call as partial feedback. And the paradigm that deals with this is typically called as multi-armed bandits, where you kind of think of these actions as arms, and then you kind of want to pull the arm that gives you the best kind of reward, right? So you want to give the treatment that gives you the best effect with respect to patients' healthcare and so on, right? So I'll talk about why it is called as a single state in a minute. So there is another set of another paradigm online learning, which is what we'll call as partial feedback, which is multiple states, which is the standard reinforcement learning setup, where again you have you want to make a decision and then you observe some feedback. Think of this as a robot trying to navigate in a space, and then it has 4 different options at every different point in the grid that it is currently in. It can either go front or back or left or right. So now it has to make a choice. It chooses one of these actions and takes a step in the direction that it chooses, and then it receives the feedback. This could be like it probably maybe ramps into a wall, or it goes through an opening and things like that. So there is some feedback that the environment provides, and based on this feedback, it now has to update its policy, so to say, how to act in different states and so on, right? So now the difference between the healthcare problem and this problem is that here you have every time I take an action, the robot's world view changes, right? So it goes to a new world, a new position in the grid, and then the action that it has to play in this new world might be entirely different from the action that it has to play in the old world where it came from, right? So that's these new positions are what are called as states, and there are multiple states, and hence I call reinforcement learning typically as partial feedback with multiple states. So in this talk, I'm going to focus on the first part, which is the full feedback setting, online learning. And then towards the end, if I have some time, I'll probably talk a bit about the partial feedback case. Okay, so the problem that we'll start off with is a warm-up problem, where again, you want to invest in a stock. There is a single stock where you want to decide whether to invest or not. Every morning, you make a decision whether to invest or not. And you have 100 different experts, let's say, who give you an advice whether to invest or not invest, right? Some people say invest, some people say don't invest. And then you have to aggregate these experts' advice and make a decision, right? So at the end of the day, you receive the true feedback, whether the stock price went up or went down, right? So if you invested and it went up, that's a good thing. If you invested and it went down, that's a mistake. If you did not invest and it went up, that's still a mistake because you lost an opportunity to make money. Whereas if you did not invest and it went down, that's still okay, right? So you prevented yourself from a potential disaster, right? So your goal as an algorithm is to somehow aggregate these experts' opinion to play or to make choices in a good fashion such that you make as less mistakes as possible. That mistakes is the way that I defined just before. Now, so now just for fun, let's assume that there is among the friends that you are asking, let's say these 100 experts, there is one guy who is a stock market guru, right? So he's somebody who knows the dynamics of the stock market so well that he predicts the answer correctly every single day. Unfortunately, you don't know who this particular person is. Of course, if you know who this stock market guru is among your friends, you'll always follow his or her advice. But you don't know who this guru is. Now, the question is, knowing that there is a guru like this among your friends, how can you aggregate the information that each of your friends are providing and make a decision every single day, right? A natural thing to do is on the first day, what you do is you have these bunch of experts giving you some answers. And what you can do is you can go with the majority, right? So let's say the majority said invest, and then you invested in the stock. And it turned out that this was wrong, right? So at the end of the day, the stock price actually went down, which means you immediately have information that the stock market guru is not in the majority, right? So which means you can remove the majority out of consideration the next day. And then you can only go with the minority, right? So which means every time you are making a mistake, you are removing at least 50% of the experts from consideration, and only the remaining people are those whose advice you need to consider from the next day, because you know that the stock market guru is among them, right? So now if you keep doing this and do the analysis, it is pretty clear that every time you make a mistake, you are removing 50% from consideration. And so if you ask the question, what is the maximum number of mistakes that you would end up making? It is pretty clear that if there are k experts, then you will at most make a logarithm of k mistakes, right? So where k is the number of experts that you are asking questions for. Now, this is very good. I mean, the logarithm grows very slowly, so the number of mistakes that you're making is not going to be too many. But there are two fundamental problems with this approach. The first problem is that, we made an assumption that there is an expert who always gets it right, which might not be reasonable in practice. The second thing is that even if you assume that there is such an expert, he or she is not going to maybe give his answers to you, right? So he'll make money himself rather giving the advice to you. So this is not a very reasonable assumption to make, right? So now we'll change the assumption and ask the question, we still have 100 experts, but no expert is necessarily a guru, right? So every expert is fallible, so they can make mistakes. Now we ask the question, how do you aggregate and how many mistakes will your algorithm suffer, right? So now, before even going and developing algorithms for this particular problem, we need to understand, is it even reasonable to try to minimize the number of mistakes in this setup, right? So the reason I say this is because potentially, if the environment behaves in an adversarial fashion, in the sense that no matter what algorithm you use to aggregate the expert's opinion, let's say on day one, you plan to invest. If you have an adversarial environment, and then it could so happen that the true answer can always be the flipped version of what you are trying to do, right? So if you invest, let's say the stock market goes down. If you don't invest, the stock market goes up, right? So this is what I mean by an adversarially behaving environment. Of course, it does not happen usually. But then if you want to analyze the adversarial setup, then it means that if you only care about the number of mistakes, then there is no way that you can control the number of mistakes because your environment could potentially be adversarial. Remember, in the previous case, when there was a stock market guru, this could not happen because the environment was constrained to make sure that at least one of the experts' answer is correct. Now we are removing that constraint, and so the number of mistakes could be potentially unbounded, right? So in this case, what do we do? So in this case, then asking for minimizing the number of mistakes is not a great idea, right? So you will never be able to minimize the number of mistakes. Instead, what happens in online learning is what is called as competing against the best expert, in the sense that the performance measure is with respect to something that we call as a regret, which we will define for an algorithm after some number of t rounds, right? So this is the number of mistakes that our algorithm, whatever algorithm we come up with, makes after t rounds, minus the number of mistakes that the best possible expert makes after t rounds. Which means if you have a bunch of experts who are all dull, right? So in the sense that they're all going to make a lot of mistakes, then, well, there is no way that your algorithm can make lesser number of mistakes, right? So the best thing that you can hope for is to be as good as the best possible expert, right? So, and this is what we'll call as a regret. So it's called regret because you are regretting the fact that if you knew beforehand who is the expert who will make the least number of mistakes, then you could have simply followed his or her advice. On the other hand, you have an algorithm which chose to make certain choices, and what we are regretting is the extra number of mistakes that the algorithm makes with respect to the best expert in hindsight. That is what we'll call as regret. And now the question is, now that we have this performance measure that we want to somehow manage, now we ask the question, can we develop algorithms which have sublinear regret, right? So as the number of rounds grows, we want the number of mistakes or the regret of the algorithm to not grow with t linearly, but then sublinearly, maybe square root of t, maybe logarithm of t, and so on, right? So remember in the previous stock market guru case, the regret was simply logarithm of k because the number of mistakes made by the best expert was 0. So the regret boils down to simply counting the number of mistakes, and this we showed was simply logarithm of k, right? So, and that does not depend on t, which is extremely good, which means that on an average, the per round regret that you suffer, right, is logarithm of k divided by t, and this goes to 0 as t goes to infinity, and which is a very good thing to have. But of course, this is an unreasonable assumption, as we just argued. So the question is, can we still come up with algorithms with sublinear regret, even if you assume that there is no stock market guru? Turns out the answer is yes. And the algorithm is extremely simple, and I'm giving you one version of this algorithm. There are multiple versions. This algorithm is called as hedge, and this is again hinting at the hedging in stock markets, if you know some stock market terminology. So basically, the idea is simple, right? So you maintain some weight over all these experts, and whenever an expert makes a mistake, you reduce the weight of this expert somehow exponentially, right? So this is the idea. In the previous case, you can think of it as maintaining a weight over experts, and whenever an expert makes a mistake, you set the weight of the expert to 0, right? So you could confidently do that because that there is a good expert that you know will always get it right. In this case, you cannot do that. So you reduce the weight of the expert exponentially, and the weight of the good guys kind of keep increasing relatively. And once you have these weights, you normalize the weights and convert it into a probability distribution over these experts. And now at every round, you sample something from this an expert from this probability distribution, and then you just go ahead with the advice of this particular expert. So this is the algorithm, right? So basically, it's kind of a weighted majority, if you will. And then you convert it into probabilities and then do a randomized version of the algorithm. So what can we say about this algorithm? It turns out that the regret of this algorithm is indeed sublinear, and it can be shown to be something like square root of t, and with the dependence again on the logarithm of the number of experts as well, which is very good because over time the per round regret kind of goes down to 0. Now the question is this the best that you can do? Are there other algorithms which can be much better than this, right? So it turns out that this is also an optimal algorithm in the sense that you can show a lower bound for this problem that no matter what algorithm you have, you cannot do better than something like square root of t, right? So in that sense, this algorithm is also the optimal algorithm for this problem. So which is good. So now this is all basic setup. So what we want to do is we want to take the same framework of competing with the best expert and apply it to several other problems. To do this, we need to look at the same problem in a slightly abstract framework, right? So what we did here was, so for instance, at one round, let's assume there are only 5 experts for the sake of exposition, and experts suggest yes, no, yes, yes, no, right? So first expert says invest, second expert says don't invest, and so on. And now as an algorithm, we maintain some distribution over these experts, and we pick one of these experts from this distribution, which is, let's say, expert 2, and who says no, which means we will not we will not do an investment. But at the end of the day, the true value is revealed, which happens to be yes, in the sense that the stock market indeed went up, right? So now we will assign loss of 1 for this algorithm, because the algorithm made a choice of no, but then the truth was yes, so there is a loss of 1. Now you can convert this into based on the output of the true value, you can also think of this as a loss for each of these experts, right? So whoever said yes gets a 0 loss, whereas whoever said no gets a 1 loss, right? So that is what this is what has happened now. Now you can also think of the same problem equivalently in a slightly different way as follows, right? So instead of saying that the algorithm maintain a distribution over these experts, picks an expert and so on, we can think of the algorithm as making a choice among 5 different vectors, right? So these vectors are simply the basis vectors. So each expert, now you can think of it as corresponding to a basis vector. The first expert is 1, 0, 0, 0, 0. The fifth expert is 0, 0, 0, 0, 1, and so on, right? So these are the choices A1 through A5. Now, the algorithm does not care there is an expert who is giving something and so on. It just makes a decision among these 5 different possibilities. And now, now we'll encode the difference between the expert's answer and the true value as simply a loss vector, right? So we will assume that we are revealed this loss vector. Instead of revealing the true value of the stock and then comparing it with what the expert said and so on, we will abstract that out and say that we'll simply be revealed a loss vector, which in this case happens to be 0, 1, 0, 0, 1. And then in this case, whatever the loss that the algorithm suffers is simply the dot product between the choice that the algorithm made, which is one of these 5 vectors, and the loss vector, right? So in some sense, the loss is linear in terms of the choices, right? So we now have kind of made this problem simpler in some sense, in the sense that we just have a bunch of options. We are encoding it as the basis vectors, and we are picking one of these basis vectors. We get a loss vector, we suffer a linear loss, right? So this is how we have changed this problem. So what is the idea behind changing this problem to this setup? Why do we care, and what's the use of this? Now we'll think of the regret in the usual way as the algorithm's expected loss in T rounds. There's an expected loss because the algorithm is maintaining a probability distribution over these 5 different vectors. And we'll compare it with the minimum loss of playing a single vector in every single round, right? So which is like following a single possible expert. I mean, this is the equivalent of whatever we said as regret in the previous case. So what happens now is that essentially, so if there were only 2 experts, basically what we are doing is maintaining a distribution over these 2 experts, which can be thought of maintaining as a point in this in this particular one-dimensional or rather 2-dimensional simplex. Whereas if you had 3 experts, basically our probability distribution over these experts can be thought of as maintaining a point in this 3-dimensional simplex and so on. And basically what the key operations that we have here is that, so at every round, you are maintaining a point in this probability simplex, and you are choosing an expert by decomposing this point as a combination of the points, the extreme points of the simplex, which are simply the experts vector corresponding to the experts. So this is one operation that is implicitly happening. The other operation that is implicitly happening is that, so every time you have a probability distribution, you update the weights, you might go out of this probability distribution. Now you have to bring it back to this probability distribution. And that is simply by doing a normalization in the standard case, right? So all we did was normalization. These were all implicitly happening in whatever we were doing. And now why does this help us is because now if you can use this framework to tackle other problems of interest. For instance, now if you have a problem where you have a bunch of factories which has certain products and bunch of consumers for this product, and let's say each of these factories has certain number of goods that it can send, and each of these consumers have a certain number of requirements. Now the sum of these 2 things are the same. So now you need to somehow send trucks from factories to these consumers you need to do this schedule. So basically, for instance, you can pick a bunch of routes and then send trucks over these routes, right? So and then you decide how much to send in each of these routes. For instance, the 4th factory, let's look at one of these factories. The first factory sends all its 10 to the first consumer and so on, right? So now the problem here is that so once you make this decision, it's an online learning problem like before. Once you make this decision, your cost is revealed, right? So after an allocation is made, this might be based on the traffic in this route, and maybe there was rain in one particular route and so on. There is a cost that gets revealed after the allocation is made. The problem is that there are exponentially large number of ways of allocating these factory goods to these consumers using these trucks, right? So you can think of each of these as one vector in some exponentially large simplex, and then you can still maintain a probability distribution in that particular simplex, right? So this is possible, but then because of the exponential size of your action space, the hedge is still an optimal algorithm, but it's not a feasible algorithm. You cannot maintain a distribution over, let's say, n factorial things and so on, right? So though hedge is good, it cannot be run in these practical setup. So this is where we kind of want to understand, can we think of some other low dimensional representation where we have a linear loss, right? So for instance, in this case, if you think of this allocation as, instead of a point, every allocation gets a separate basis vector. Instead of that, if you think of allocations as simply a matrix, which is the number of factories cross the number of consumers, and then you just put in each of these rows the amount that was sent from each factory to each particular consumer. So this is an m cross n matrix. And now the cost is for each of these routes that you chose, right? So, and now you have a linear relationship between the amount that the algorithm suffers is just the dot product of these two matrices. So now, what are our action spaces? All valid integer transportation matrices are our actions, and cost becomes linear in this representation, right? So now, essentially, now you don't have a simplex anymore, but some complicated convex combination of all these transportation matrices, which is the space where you are maintaining some distribution, right? So for instance, every point in this complicated polytope, which is called as the transportation polytope, is a probability distribution over allocations. And there are potentially, in this case, n factorial, but I mean, it could be potentially exponentially large number of allocations. Now, how do we deal with this problem? So we need to deal with two problems, right? So given a point inside this polytope, you must be able to efficiently decompose it into some convex combination of its endpoints. That is problem number one. The second thing is that when you update the weights somehow, the point might go outside this polytope, and now you'll have to bring it back into the polytope by making this projection. So there are these two operations which we somehow have to come up with for this particular problem. Now, how do we do that? Well, this is where famous theorem in convex analysis comes into help, which is called as the Caro-Theodori theorem, which says that, well, no matter how many points you have, if you take the convex hull of these points and look at any point in the convex hull, it can be decomposed as some convex combination of not too many endpoints, right? So maybe you have exponential number of vertices, but then every point inside the convex hull can be decomposed as a convex combination of a small number of extremal points, right? So even though you have exponential points, each point can be decomposed using polynomial number of extremal points. This is what this theorem says. Now, how do we use this theorem in our setup? So in this case, it so happens that if you take any point inside this polytope and then look at the induced graph for this polytope, where there is an edge between a factory and a consumer, if there is at least a fraction of items going from this factory to the consumer. So if the point is inside the polytope, one can show that this graph will always have some kind of a loop, right? So there is a loop in the graph implies that the point is inside the polytope. Now you can use the fact to cleverly remove these loops to somehow decompose this every point inside the polytope into a convex combination of these extreme points, which means these extreme points are our allocations, and we need to maintain a distribution over these allocations, and we can do that efficiently, right? So that is the decomposition part. The projection part is typically easy, right? So the way you do it is if something goes outside this polytope, then we know that the row sums and the column sums of this polytope have some fixed values, and then you can do some alternate row and column normalization to get this right? So, and now once you have this decomposition and projection algorithms, now you can talk about the regret, and it turns out that we can show that the regret of this particular algorithm, this is an efficient algorithm, whereas hedge was not, and still you can talk about square root of t regret for this problem, right? So this is what I wanted to talk about online learning. So putting it all together, what I wanted to say was in an online learning setup, you want to identify the actions in your problem. And if you have a large action space, if you don't have a large action space, then you can use the hedge algorithm. Whereas if you do have a large action space, you can try to think of, can I represent my loss as a linear function in some low dimensional action space? If you can do that, well, then you'll have to develop some efficient decomposition and projection routines. If you cannot do that, then, well, the problem is slightly harder. You need to have more specialized routines, right? So this is the high level overview of the online learning problem. So in another 2 minutes, I'll take 2 more minutes to quickly talk about the other problem, which is the multi-armed bandits problem, where the goal is to nab what we call as opportunistic criminals, right? So here the problem is you have a bunch of policemen and you have a bunch of cities and you want to allocate these policemen to cities. And the way you do that is the first day you make some allocations and then you observe some crimes. And in the second day you make a different type of allocation, you observe some crimes and so on. So the way we are trying to model this problem is the goal is to allocate patrol efficiently over time. And the way we make this allocation is as follows. So we first have to assume that what is a model for these crimes. We are thinking of these criminals as opportunistic criminals in the sense that they don't really think too much before trying to commit a crime. These are petty criminals such as people who do muggings or do traffic violations and so on. Basically, what we do is, let's think of this as a single patrol officer for the moment, and who spends 10% of time in location 1, 30% of time in location 2, and so on. This is the allocation that we make. And there are these petty criminals who have a coin in their hands and with different biases. The first criminal has a coin with 0.6 bias, the last criminal with 0.7 bias, and so on. The criminal tosses the coin, and if it falls yes, then he decides to commit a crime. He decides to attempt a crime, right? So this is the latent decision of the criminal. And now what we observe is whether he indeed committed the crime or did not commit the crime, right? So this is our observation. We make an allocation and we make an observation. Now, what is the difference between the latent decision and the observation? The difference is that whenever the criminal decides not to commit a crime, there is no crime. On the other hand, whenever the criminal decides to commit a crime, well, he will go ahead and commit the crime only if the allocation of the policeman is not too much, right? So only if, let's say in this case, if the allocation is greater than 0.5, then he won't commit a crime, right? So which means in these cases, when the allocation was less 0.10 and 0.1, he went ahead and committed the crime, whereas in the other cases, he does not. So this is our model of criminals. Now, the fundamental trade-off here is that is what we call as censoring, because if no crime happens in a location, you now are in a fix, right? So it was either because the allocation was good, you put a lot of police officers, and there was intent, but then it got suppressed because there are a lot of police officers, or there was no intent at all, right? So there was the inherent chance of a crime happening itself is less, and now it becomes tough to balance these two things, and this is what is probably the problem of censoring. Right? So now how do we solve this? Well, without going into the details because of the lack of time, so I'm going to say that you can do some kind of a binary search type procedure to estimate the sensitivity of the sensitivity threshold of the criminals, and then you solve something called as a knapsack problem repeatedly for this problem. Now the problem becomes tougher when each location has a different sensitivity threshold. I won't really talk about that. I'll just going to end this by referring you to two different papers based on which the talk was about. The first one was NeurIPS 2014 paper, which was online decision making in general combinatorial spaces. When you have a combinatorially large set of actions, how do you deal with it? And the second paper was, much recent work, which is on censored semi-bandits. Right. So yeah. So with this, maybe I'll stop and take any questions. Thanks.
Hello.
Yeah.
Sir, one of the attendees would like to know how the maximum mistakes is log k when the number of experts is k.
Okay. So so let's say you have 100 experts, right? And in the first day, 70 people say yes, and 30 people say don't invest, right? So now you go ahead and invest, and it becomes a mistake, right? So now, which means you know that the stock market guru is not in the 70; he must be necessarily in the 30, right? So you can remove all these 70 people from consideration. You only retain the remaining 30, right? So now the next day you only take the advice of these 30 people and go ahead with the majority of these 30 people, right? So and if the majority is wrong, you will at least remove 15 people, right? So now if you ask the question, what is the worst case that can happen? So every time half the people say yes, half the people say no, and you are removing half the people from consideration. Every time a mistake is there, you are removing half the people. Now you ask the question, how many times how many mistakes can I make before I zoom in on the single expert? And if you just work it out, because you are exponentially reducing the number of experts in consideration every time, So it is going to be, so you'll ask the question 2 to the what equals the number of experts, and that what is the number of mistakes. And that turns out to be simply the logarithm of the number of experts. Hope that clarifies.
So we have a couple of more questions.
Sure.
So this question is from Deepan Murwani.
Yeah.
If we can define decomposition and projection efficiently, even when we have large action space, can we still use hedge?
You can use hedge. The problem with using hedge is implementation, right? So you might be able to define, I mean, if efficient decomposition and projection algorithms, so what do you mean by efficient, right? So efficient is, so given a point in this large combinatorial space, as long as you can efficiently decompose this into a convex combination of the endpoints, then you're fine, right? So if you can do that, you'll always be able to do that. But in the standard hedge, you are going to assume that your action space are vertices of a simplex. And if you have combinatorially large number of items, then it's going to be a combinatorially large simplex, right? So it's let's say an n factorial size simplex. In that case, there is only one way to decompose. Every point is simply a trivial decomposition, right? So if you, let's say it's a 3-dimensional simplex with 0.1, 0.4, and 0.5, then it is trivially 0.1 times 100, 0.4 times 010 plus 0.5 times 001. And that's the only way you can do that, right? So in those cases, you simply cannot do that because you might have exponentially large number of experts, exponentially large number of endpoints whose combination is what you're maintaining, right? So, if it is a simplex, there is an issue when you have a combinatorially large number of space, and hedge works with simplex, and that's why you need slightly different algorithms.
Thank you, sir. We have another question from Rajiv M.A. Feedback from yesterday is not the same as the feedback from a month ago. Did you incorporate some sort of time decay in the feedback to handle this non-stationarity?
That's the whole beauty of the algorithm. You don't have to do that, right? So, the reason being that you are not trying to compete with by making as much money as possible, right? So that's not what the goal was. The goal was to make as much money as the best possible expert, right? So if the trend changes, maybe there is one expert who's performing well in the first 1,000 days, let's say 100 days, or maybe 1 month, and the next month a different expert performs better, your algorithm automatically adjusts to the shift. You don't have to do anything specific, right? So because the first expert's loss is going to increase because he's going to do worse in the second month, and the second expert's loss is going to decrease because he's going to do well, the algorithm automatically adjusts. If you think of it as what happens in the probability distribution, you are maintaining a point in the simplex and you are moving towards one of these endpoints. Now, if a different endpoint starts performing well, your point kind of automatically shifts to the other endpoint. So that is automatically encoded in the algorithm. Of course, if you know some dynamics, you should always try to incorporate it. Here, we are assuming that we are oblivious to the modeling the underlying dynamics of how these stocks perform.
So we'll take another final question.
Oh, sure.
What would be the real life interpretation of the decomposition in the traffic problem?
So the decomposition is, so essentially your algorithm is maintaining a distribution over all possible allocations, right? And now, what does it mean to say I'm maintaining a distribution over all possible allocations? So I'm maintaining essentially a convex combination of these allocation matrices, right? So this will be a fractional matrix that I'm maintaining. Now, given this matrix, I cannot send fractional goods in this particular case, let's say, right? So I can only send integer valued goods because these are goods, right? So I need to send 10 in one. I cannot send 10.5 packets, right? So that is the issue. So now you have to somehow decide what is the allocation that I need to exactly make. And in this case, it so happens that if you have a fractional allocation matrix, now you have a problem of decomposing this into a distribution over integer allocation matrix, right? So once you have that, then you can sample one of these integer allocation matrices and then use that as your scheduling, right? So now, so that is the main issue of decomposition, right? So you are maintaining a distribution over allocations, equivalently you are maintaining a fractional allocation matrix, but that is useless in practice. In practice, you need integer allocation matrix, and hence the necessity for decomposition.
Thank you, sir. Thank you for the great talk.
Sure, thanks.
Our next talk will be given by Dr. Bhargava Rama Chilukuri. Dr. Chilukuri is an assistant professor in the Department of Civil Engineering at IIT Madras. Prior to this, he was a postdoctoral fellow at Georgia Institute of Technology. His research interests include traffic flow theory of homogeneous and heterogeneous traffic, optimal control of arterials, highways, and networks, numerical methods, and simulation. Over to you, sir, for the talk.
Thank you, Mohit. Let me share my screen. Can you all see the screen?
Yes, sir.
Okay. Good. So, just, okay. So, yeah. So the talk is going to be a little different from what we have heard till now. So, good morning, everybody. So I'm Bhargava. I'm an assistant professor in civil engineering. So today I'm going to talk about Wi-Fi sensor data for traffic applications. So traffic data is very critical for developing transportation models, algorithms, and applications, as well as for real-time control and management of traffic. So these sensors give us traffic data. The traditional sensors that we use in traffic engineering are mostly the location-based sensors. So what I mean by location-based sensors is the sensors that are installed at the side of the road or at a fixed location, and we collect data using these sensors. So the traditional sensors like cameras or radar sensors or the Bluetooth sensors or the infrared sensors, these are the standard sensors that traditionally transportation researchers have used. But these sensors are very expensive. They are tedious to install and maintain. And also they give only location-based information. So these sensors look at one particular location and they measure the speed of vehicles or the flow of vehicles at that particular location. So we don't have information of spatial propagation of vehicles and traffic states. So every sensor is giving us information only at that location, and we don't have any information of what is happening between two sensor locations. So in essence, the traditional sensors are costly and arduous. So one alternative to these sensors is to actually get spatial information using different set of sensors.
Hi, this is Karthik. Could you just switch your slideshow? We have the display being shared.
So really? Okay. I wonder how sorry.
No, just share again. Just share again and say duplicate slideshow or something. Also, it should be fine. You have a dual monitor setup, I think. So
yeah, I have dual monitor.
You just have to swap display settings. You swap to the other one. Just share the presentation. At the top, you will find the display settings.
Share screen 2 problem.
Get into presentation mode.
How about now?
Yeah.
Perfect.
Okay, good. So I apologize for that. So the traditional sensors are costly. So what we need is a new set of sensors which will give us spatial information, because spatial information is extremely useful. So we'll have much more information and understanding of what is happening within any given segment. So these spatial sensors or spatial data will help us characterize the operational performance of different road sections. So we'll be able to know what is the speeds within the sections, what is happening within these sections. So why is this useful? Because we all know, we all use Google and other service providers which give us travel time information, right? So this information can help us make judicious decisions about what route to take, what mode to take, or even decide on when to leave from a given origin. So all these things can be possible only if you have spatial information. If you have location-based information, it's very difficult to extrapolate to spatial information. So spatial information is extremely useful. And how is this done? This can be done by re-identifying the vehicles at different locations, right? So if you are measuring at 2 different locations, we identify a vehicle at this location and again re-identify the vehicle at another location so that we can estimate what is the travel time it has taken to traverse that segment, right? So this is what is traditionally done. And how is it done? It is done through automatic license plate recognition. So you have license plate recognition softwares which are continuously looking at license plates, and then the information on the license plate is matched at different locations, right? And RFID tags and GPS technology. So if you have RFID tags on the vehicles, then you will be able to get what time it crossed a sensor location and again at another sensor location. Similarly, if you have GPS, you have continuous tracking of vehicles, so you know what's the travel time it has taken and how it has propagated or how it has moved through the section. So all these things are traditional approaches that people use to get spatial information. However, these have challenges, right? Especially in the heterogeneous traffic scenario, like the one that we have in India, where we have different vehicle classes. Things are not standardized as well, and vehicles move in, without any lane-based approach, right? So they all move in different lanes wherever there is gap, especially the two-wheelers move very randomly through the network. So these technologies have significant drawback or significant limitation when it comes to heterogeneous traffic. So the license plates, for example, in India are not very well standardized, especially the positioning of the license plates or the background or the text size. So all these things make it more challenging to use the traditional automated license plate recognition softwares. Similarly, RFID tags and GPS technologies, you need a lot of vehicles to have these things on so that you can get a significant amount of sample, right? So these things make it a little challenging for heterogeneous traffic conditions to get spatial data. So one of the possible solutions is the MAC sensors. So the Wi-Fi sensors or MAC sensors, as I'm going to call for the rest of the presentation, these are one of the potential sources for getting information very easily. So what these do is these sensors capture the MAC addresses of electronic devices as the devices pass by, and you use these MAC addresses to re-identify the same MAC address at different locations, so you can actually get travel time between 2 different locations. So that is the basic idea. So you have MAC sensor. I don't know if you can see my mouse pointer. Can you see the mouse pointer?
Yes, sir, we can see your mouse pointer.
Okay, good. So you have a sensor on the roadside, which is in a box. And then as the vehicles pass by, and the vehicles have these devices, for example, your mobile phone or an entertainment system which has which uses Wi-Fi. So if this Wi-Fi is on, it actually captures the MAC address of these devices. So in effect, if these devices are on the vehicles or in the vehicles, so you actually know the identification of the vehicles. So you know the vehicle and you can match the MAC address at different locations to get the travel time. So the advantage of these sensors is that it allows for non-participatory tracking, right? So you are not interfering with the traffic. They are sitting on the roadside, passively observing the data as the vehicles pass by. So you capture the vehicle or the device MAC IDs as the vehicles are passing by, and you are not actually influencing the driving behavior or the driver's behavior. So typically the cameras, for example, when they are mounted on the poles, they are looking at oncoming traffic or leaving traffic. There is a possibility that vehicles get more conscious or drivers get more conscious, and then their behavior changes because there is a camera in place, right? So here, these Wi-Fi sensors are sitting on the roadside in a box, totally not visible to drivers. So they have no idea that they have kind of been tracked or they are observed rather. Right? So, however, I mean, again, we are only getting the MAC addresses, and there are ways to make sure that the privacy of the devices and the drivers is taken care of. So that is one part I'm not going to talk about, but that is a possibility. So we are doing that. So there is, even though the people are not aware that their MAC addresses are being captured, we have systems in place so that we don't actually collect any personalized information. Okay. So with the MAC addresses captured at these locations, we match the MAC addresses at different locations to obtain the travel time. And we can also use these sensors to get a better understanding of where the trips are originating, where the vehicles are starting, and where they are going. Right? So this can be useful for other transportation applications. So these sensors are developed. They are developed a few years ago. So there are several commercial sensors, for example, the Cyclica, Road Trend, the other one, Michelin and Bilip Track. These are all software devices developed commercially. They cost around 1,200 to 2,500. So these are pretty expensive scanners. So what we did at IIT Madras was the ITS lab that we have here at IIT Madras. We developed a low-cost Wi-Fi scanner to do exactly the same thing. So this sensor does exactly what the commercial sensors do, but at a much cheaper cost. So we developed the cost of our sensor is about $90. So you can see here it has a Raspberry Pi with the scanning module, and then the Raspberry Pi is here, and then you have a fan, and then the radios and antennas and adapters to transmit data and capture data. So this is a very simple setup that was developed at IIT Madras, and RBCDSAI actually supported. This was the research on this data set actually started with the exploratory research proposal funded by DSAI. So the first project that we successfully completed, the data analysis and traffic state estimation using Wi-Fi based sensor technologies, that was supported by DSAI, ended last year. So during this project, we actually started using these sensors and trying to see how well we can capture data, what is the quality of data, what is the quantity of data, what are the characteristics of these sensors, and what are the possible applications. We started exploring all these things during the project. So I'm going to briefly talk about that project to begin with, and talk about possible extensions that we are, extensions of those things that are ongoing, and also other applications. So what we found during the process was the Wi-Fi Mac sensor, as the speed increases, the devices spend lesser time in the vicinity of the sensor, right? So for example, if I have a car moving at high speed, it spends very little time in the range of the sensor. So there is very little possibility that you will actually capture. So it's not that every vehicle, every device will be captured. So there is, depending on the software that is there on the device, we will be able to capture the device depending on the duration it spends within the vicinity of the sensor. So for example, if you see here in this plot, here you have different modes, for example, car, two-wheeler, walk, and bus, and the number of detections. So if somebody is walking, he's going at much lower speed, so you capture the MAC ID. So there's a very high probability that MAC ID will be captured, right? Similarly, if you have bus, similarly, if you have here car, it is going faster, so it captures less, but two-wheeler is going even faster, so you capture even lesser, right? But you would wonder why bus actually that goes slower captures much lesser. So this is an interesting problem. So we found out that it has much harder, so it has a lot of impedance because of the structure, as well as there is possible interference between multiple devices that are there in the bus. So the research is ongoing to actually find out and why it is happening and how we can overcome this limitation. So this is the characteristic. So as the speed increases, you have less probability of actually capturing the devices. And here this table shows a sample of the data. So all we are capturing is the time at which this device MAC address was captured. So the MAC address, the time, and the strength at which this device was captured. So the signal strength of the packets received from this MAC ID, right, at the device. So also another thing that we found was, as the device moves away from the sensor, the signal strength decreases logarithmically. So this is another thing that was there in the literature, but we also found out it was happening in the Indian context, and it was true for all vehicle classes. So consistently it decreases with distance. So a simple performance, I'm not going to, we did a lot more evaluation, but to give you a simple overview of what we did. So we actually did cameras. We put cameras, we measured the number of vehicles that were traveling on the road, and we looked at how many unique MAC IDs that were captured. We got around 40 to 50%. At this location, we got 53, which was the highest on Velachery main road. But we found out that especially on OMR, which is here in Chennai, where you have a lot of electronic IT companies, we found out that there is huge penetration. So penetrations up to 40–50%. So you're able to capture samples of about 50% of the population. So which gives us a lot more confidence in the models, right? So you have enough data to actually do data-driven models, or you can have systems which are more reliable because we have higher sample size. So, and we also found out that the sensor that we developed in IIT Madras outperforms commercial sensors in terms of the number of MAC addresses captured. So overall, it looks like, I mean, it was kind of confirmed that the device that we developed at IIT Madras and supported by DSAI was working very well. So as a part of the project, we installed these sensors at different locations. So if you are familiar with Chennai, you will see that this is SP Road. So this is Little Mount coming to SP Road, Anna University, and then this is OMR, and then this is Taramani Road, and this is 100 Feet Road and back to SP Road. So we installed several devices around IIT Madras. IIT Madras is here. Okay. So we installed around IIT Madras, and we did some evaluation. We found out that these are all different locations, the device number. So these are device numbers. And then on the y-axis, you have the number of MAC IDs captured. So you can see that we got up to almost like 38,000 MAC addresses. Right? So you can see here, we captured about 38,000 MAC addresses at this location, 104 in a day. So which means that about 38,000 vehicles were captured. So which is over 1,200, 1,300 vehicles per hour. Right? Similarly, at different locations, we captured different, but on average, we found out about 500 to 1,000 vehicles per hour, which is pretty significant sample. And which you can see that over multiple days, multiple months, you can see the amount of data that you can actually capture. So this is very rich data, and for developing data-driven models as well as for any kind of analysis, traffic analysis. Right? And again, we looked at how the data is distributed in a day. So you can see that it's not that most of the data is captured only at one particular time of the day. So this is the time of the day as well as the number of MAC addresses, unique MAC addresses captured. So you can see that initially in the morning, you have very less traffic. So you're capturing less. As the time goes by, the peak hour picks up. So you have many more MAC addresses picked consistently during this period. And then during the afternoon off-peak period, you have lesser because you have lesser traffic on the road. Again, picks up in the evening and goes down. So you can see that it's consistently capturing data all through the day. And we also looked at how this data can be used. So I am going to show you quickly one particular application, but this data is very rich to do several things. Here is one application that we have done as a part of the exploratory research project. So we looked at how this data can be used to estimate mobility in the network. So how the speeds are varying or how the travel times are varying on different segments of the network. So what we are seeing here, what you are seeing here is the color coded. So the blue lines, so each of these bars are for each location. So each segment you may call, right? So this is for one segment, this is for another segment. And the blue represents, so if this is for one day, how many hours of the day you have speeds less than 20 kilometers per hour. If it is orange, it is 20 to 40 and 40 to 60 and more than 60. Right? So this is the color coding that we have used in this study. So you can see that you have different segments. Each segment performs differently. So the travel times are different. The speeds are different on each of these segments. Why is this useful? This helps us to get a spatial sense of how the congestion is distributed in the network, how different links are performing, in sense how the travel times are, speeds are different on different segments, where are the bottlenecks, so that this can help you to figure out or plan your maintenance as well as operational strategies, as well as give people guidance on which route to take or which mode to take, and so on and so forth. So you can help in both planning aspects as well as the operational aspects and traffic management also. Right? So if you see that some locations suddenly something changes, you may, I mean, I'll talk more about it later on, but you may identify it as a potential incident and try to explore and try to clear the incident, right? So the understanding of what's happening on these segments is extremely useful. So here I'm showing few plots. So this is the monthly data. So if I'm looking at 1 month of data, right? So you have 1 month. So you are looking at how many days of August it has speeds less than 20, 20 to 40, 40 to 60, and so on and so forth. So, and you have different segments. So Madhya Kailash to Lemon Tree, second footover bridge on OMR to Madhya Kailash, and so on and so forth. These are the different segments that I have shown in the earlier plot. So you can see that these first two and the last two have very small blue segments, right? So which means that these are performing well. So these sections have less traffic, I mean less delays, so you have higher speeds, right? Whereas if you see here, the Velachery bypass to TCS, it has huge blue band, which tells you that significant amount of days this location has congestion. Right? Just to give you a simple example. Similarly, if you are looking at weekly data, you can actually see how it is consistent across different days, right? So across different weeks of the month, you can see that this location consistently shows higher blue bands compared to other locations, and these locations give you are consistently giving you smaller travel times. And if you look at daily, you can see that, for example, 4th, which is Sunday, right? 4th and 11th, 18th, these have much lesser blue bands compared to the other days. At Monday compared to Monday, Sunday, you can see that it's much lesser, and then compared to Friday. So Sundays are generally better, but there is one day, August 29th, something happened. So you can actually look at consistently, if you are monitoring this data in real time, you can see how things are changing. And then when you see something is, if there's an anomaly in the data or there's a singularity in the data, you can quickly identify it as a possible incident or something is happening, so you can take appropriate actions, right? So you can see that this data tells you that the data is rich and consistent, and looks like the data is, has good fidelity. Again, if you're looking at the daily hourly data, you can see that this is the peak hour, 5 to 7 p.m., where you have consistently larger blue bands on all the segments. Right? So there are several applications possible. I'll talk about a few more applications. So this is what we have done during the exploratory research project. Then let me go to the next application of bus arrival time prediction. So this is ongoing work. So this has, here we are trying to use this Bluetooth travel time data to estimate bus arrival time prediction. So we have buses. So we are doing this as a part of a project where we are trying to give bus priority at the intersection. So you identify a bus is arriving at the intersection, you change the signal timings in such a way that the bus has lower delay. So for this system, we need to estimate when the bus will actually arrive at the intersection. Right? So you pick the bus at about 500 meters or so, 300 meters, but then you want to estimate at what time it reaches the stop bar location, so that you can give green time till that point, so that the bus can go to the intersection. So bus arrival time prediction is the stop bar is an important aspect of bus priority system. So we are using gradient boosting method. Again, these are some of the strengths that many of you may already be familiar with, right? So we are using this method. Again, this is one of the first steps that we are taking into using this data for data-driven models, developing data-driven models. So here we have 62,000 data points. We are using so many for training and so many for testing. So here our input is, we are looking at if the signal has, so if the bus arrival is picked up at some time, what is the signal status at that time, right? So our input is, we are dividing the green and red durations into different bins, and then distance from the intersection at which the bus is picked up. Again, you have to remember that bus has a device, onboard device, right, which is trying to communicate with the signal. But if you have a large truck in the front, or if you have trees blocking the view, it is possible that the bus signal may not be captured well in advance. So it may be captured only once it gets a little closer, maybe 200 meters or 300 meters from the stop bar. So we are also looking at distance from the intersection as a input parameter, and all this speed until the current position, most recent travel times. So we are using supervised learning methodology here to estimate what would be the travel time to the intersection. So from the current position, can I predict what time it can actually reach the stop bar? Right? So, and the hyperparameters are given here. So we are dividing the green and red bins into 10 different bins. So 5 for greens and 5 for red duration. And so here you can see on the x-axis you have the time. So this duration is green duration, and this is the red duration, and again it's green duration, red duration, so on and so forth, right? So we have different scenarios. So G1 is it's green, so bus arrives in the green, so it goes through, right? I mean, we are looking at two different intersections. So bus goes through in this section, but it actually gets stopped at the next intersection, and so on and so forth. So we are trying to estimate the travel time of the bus at the stop bar using this method, and we found out that the RMSE values are pretty reasonable. It actually gives you much more error in the last 100, because there is a small error in capturing when the signal turns green versus red. It actually leads to a huge variation in what time it can reach, because the vehicles in the front will not be able to go through. For example, if you have estimated that it's green and signal turns red, the vehicles in the front may not be able to go through, so the bus actually gets stuck before it gets to stop bar for the whole cycle. Right, so it gives much more error in the last 100 meters for R1 red bin, but for others it has much reasonable RMSE values. Okay, so the next application I'm going to talk about is the ongoing research. Again, here we are utilizing the Wi-Fi sensors, but we are trying to use V2V, vehicle to vehicle communication, and vehicle to infrastructure communication to estimate traffic state in the networks. Right? So here we have devices, onboard units, which are installed on the buses, which also have the Wi-Fi sensor. So traditionally we put Wi-Fi sensors on the roadside, right? So you put, for example, this intersection, you put on the roadside in a box here. But what we are trying to see here is, can we put these devices on the buses, so to make them mobile sensors, so they are moving in the network, trying to capture MAC addresses at different locations, right? So you're capturing the MAC address as well as time, and it also has a GPS, so you know at what location, at what time, what MAC address was captured, right? So these, and then you have roadside units which actually communicate with the onboard devices. So when the bus comes in the vicinity of the onboard, in the vicinity of the roadside unit, it sends all the data to the RSU. So you can see that the buses actually capture a lot of data, because they are traveling in the network trying to capture MAC addresses from different locations continuously. And at the same time, we are not instrumenting the network extensively. We only have these roadside units at few locations along major corridors. So when the bus comes in the vicinity, it dumps all the data, right? So with sparse infrastructure, sensor infrastructure, we are trying to capture network level characteristics. So this is what we are doing right now. We plan to use data-driven models to actually estimate, because the amount of data that you get is humongous. So we have about 2 GB of data coming every day from each of these devices. So we're trying to see how we can utilize this data for different traffic applications. So just to give an overview what we are doing, this is we have installed RSUs at different locations, the roadside units at 10 different locations, and Wi-Fi sensors at other locations. We are looking at 3 different corridors, so T Nagar to airport, Vadapalani to airport, Tambaram to airport in Chennai. So we have RSUs, and then buses. We have the onboard units, the Wi-Fi sensors on buses, which will be traveling on these routes, will be instrumented. So you capture data from all these roads. So we have other projects. Due to lack of time, I'm not going to talk about all the other efforts that we have here. I mean, we are pursuing here at IIT Madras. Some of the things that we are looking at is, how do we use this data for control characteristics of networks? So how do we estimate what is the signal status, for example? So when the buses are traveling, you don't have to communicate the signal status to the centralized location. So using this data, can we estimate what time the signal turned green, what was the green duration, what is the red duration? Why is this important? Because once we have this information, we'll be able to predict the traffic conditions. So estimating is one part, but if we know how the signal is changing over time, I'll be able to estimate, or I'll be able to predict the traffic state much better. So that's one approach that we are trying to pursue. And the other thing is, can we estimate incidents in real time. So using this data, can we estimate what are the different, so when we have these travel times, you have different travel times, right? So you have to estimate what are the different types of incidents that may be happening, right? And what are the effects? So the effects are not going to be constant for every incident, right? So different types of incidents will result in different types of travel times on the road. So can we do an unsupervised learning approach to actually identify what are the different types of effects that you get because of the incidents? And other thing is, can we differentiate the congestion or the travel time differences with congestion? So congestion versus incident. Can we estimate incidents so that we can send an alert to police or incident management center or appropriate authorities so that they can go and remove the incident, right? Traditionally, people rely on people calling or people patrolling police, identifying the incident and trying to communicate it. But here you can automate things. Similarly, can you use this information to do control both at intersection level or as well as the network level, right? So can we use this data to have a more traffic responsive signal control system? And can we estimate local traffic conditions? So here we are taking travel time between two segments. So you have traffic data or travel time data between these two segments, but can we actually estimate at local conditions? For example, can we estimate the queue length, how far the queue has spilled back and things like that? Okay, so these are some of the efforts that are ongoing. And I have a lot of collaborators. Professor Lalita was part of the project that was funded by DSAI, but we have another project with the DSAI again, and we have several students also working on some of these aspects. So with that, I end my presentation. If you have any questions, I'll be happy to take.
Thank you for the talk, sir. We have a couple of questions from the participants.
Sure.
The first question from Rajiv MA is, what is the impact of weather, that is temperature, rain, etc., for the sensor output? For example, temperature varying from -20 degrees to 45 degrees. Do you expect more noise in data when weather or climate varies?
Yeah, it's a very good question. So yes, so our efforts, we have only taken baby steps, right? So we are actually trying to look at, we haven't yet understood everything about these sensors. I mean, these sensors are very useful for Indian conditions. So we are trying to explore more about these things. We have a couple of, we are pursuing other projects and other, we are actually collaborating with people from electrical engineering and other people who are more well versed with these kind of technologies to actually make these devices more robust. But yes, these do have an effect. We know for sure that weather has an effect, especially the environment has an effect. I mean, when I say environment, not only the weather, but also the built environment. So because you get more reflections and with the signals. So how do we actually incorporate the effects of these parameters, the built up environment, the weather, temperature, as you rightly mentioned. So these are things that are important questions, and we will be exploring those.
So we have one more question.
Yeah.
We have a good capture addresses of more than 50% at a particular point. Do we also have adequate overlap of the vehicles in the second point? That is, are there enough proportion of vehicles getting captured at both points?
Very good question. Right. So, so it depends. So you should understand that the device has software which actually drives a lot of this, right? So it will send out packets which will be captured by the sensor. So if the device has software, it's again, all these devices have proprietary software. So the rate at which they send out packets is going to be different over time and space, right? So if it's not capturing, basically what these devices are doing is they are trying to look for a router to connect to. So they'll be sending out packets, and this sensor is passively taking these packets and registering the MAC addresses. So the device's software, if it has a logic, for example, that if I don't see for the first 5 seconds or 10 seconds, I will reduce the frequency at which I'm sending the packets, because when it's sending packets, it's draining the battery, right? So the software actually determines what happens over time. Right? Also depends on the vehicle speed. So if the vehicle travels at slower speed in one segment but faster in another segment, you may not be able to capture the same MAC-ID again. But what we found is we get enough number of samples. And if you see the plots that I have shown, especially the speed profiles, those are not based on one or two devices. They're based on hundreds of devices. So we get significant amount of re-identification of these MAC addresses. So at each location we get thousands, but re-identification we get multiple hundreds. Definitely not all vehicles are captured, but a significant amount of vehicles are captured. I hope that answers your question.
Yeah. Thank you, sir. Thank you for the talk.
Okay. Thank you.
The final talk of the day will be delivered by Professor Manikandan Narayan. Professor Narayanan is an associate professor in the Department of Computer Science and Engineering at IIT Madras. He is also a core faculty at the Initiative for Biological Systems Engineering. His research areas include bioinformatics, computational network biology, and systems biology in health and disease. Prior to joining IIT, Professor Manikandan was a staff scientist in the Systems Genomics and Bioinformatics Unit at the National Institute of Health. Over to you, sir, for the presentation.
Thank you. Let me start sharing the screen. Can you see the slides and hear me?
Yes, we can.
Okay, thank you. So thank you for this opportunity to present in the 8th RBCDSAI workshop. And I'm excited to talk about some of the work we have done on multi-layer network models with applications to biological or biomedical data analysis. Okay, so I will start out with an introduction to some of the biological questions that are of interest to us as a group. So I'm part of, I'm the principal investigator of this bioinformatics and integrative data science group that we call BIRDS. And later on go to some two specific data science related problems that we are focusing on in aligned with the theme of this workshop. So in terms of interactions, right? Interactions is essential to biology, essential to life. So we have interactions happening at different scales. We have organ-organ interactions between the different organs in our body, and which I also sometimes refer to as tissues. So we have these tissue-tissue interactions. We have cells that compose tissues. So there are interactions among the trillions of cells within our body. And then within each of the cells, we have about 20,000 genes in humans, right? So all these genes are not on at all the time. So some of them are on, some of them are off, and they all interact with each other to control or regulate other genes. So one gene, if it's on, it may go on and switch on or off other genes, which may have a cascading effect, and further on, it may switch on or off other genes and so on. So this complex choreography is what allows us to, allows life to sustain for any multicellular organism. And we know from different fields of biology, so hormone biology, neuroscience, molecular biology, we know a lot about how these interactions are happening. They may be hormone-related interactions, neuronal interactions, or other types of interactions. And one particular example that may be relevant right now is we are close to a lunchtime. And so many of you may start getting, if you especially eat around this time, right? 12 or about 1. So then our stomach as an organ or a tissue is generating some hormones, a main of which is ghrelin. And then that ghrelin is actually doing multiple things within the body. It's generating acid within the stomach, so which makes you hungry, and it gets the stomach ready for digesting food as you eat. And then it again sends signals to the brain. So there is a particular small region between our eyes here inside of the brain called hypothalamus, which basically helps you decide, okay, is there food going to be at the end of the talk? Where am I going to eat? And so it generates this hunger drive, right? So all of these different organs would have to, and internally within the hypothalamus, it's because this hormone that is produced at the stomach is being released into the blood. It travels into the blood, reaches the hypothalamus or this brain region, and then there it activates other genes, which produces other proteins and does all the major functions in trying to figure out where your food source is and trying to generate your appetite. And even though we know a lot about these interactions, still, as with biology, so still many interactions are waiting to be found, and they are routinely found through various methods, from experimental to computational. And experimental methods are kind of detailed experiments are a bottleneck. And so we would like to see if we can analyze biomedical data. In particular, there's something called genomic data, where we consider all the genes in our human genome, so 20,000 genes that I was talking about. And there are experimental techniques which measure these genes in different tissues of the human body, post-mortem, of course, and then collected across multiple individuals. So how do you go from that data to build a map of these biomolecular interactions that is at the root of many of healthy and disease functions? Okay, so that is the major question that we address as a group. And if you want to go a little bit further, so each of us are exposed to, we have different genetic factors based on our hereditary information. We are exposed to different environmental factors. And all of these varying factors leads to slightly different gene networks. I mean, the gene information or the gene relations between you and me, right? So the level of the genes are different from individual to individual. And how do you measure that in multiple tissues? Here I'm showing kidney, heart, and liver. And once you have the data measured, which modern biology allows us to do these high throughput measurements, which was not possible before, but recently these are getting more and more possible, and more data sets on multiple tissues and several sets of individuals are accumulating. And how do you go from that data, which is essentially in matrix terms, it's a 3-dimensional matrix, with one dimension being all the individuals, another dimension being the genes that are expressed or active in these tissues, and then the third dimension being the tissues that you're measuring, right? So how do you go from that to a map of which genes are interacting with other genes, which genes are controlling other genes, and so on? And basically the premise that on this data-driven approach is the interaction between genes manifest as a statistical correlation between these genes across individuals. So in this particular case, I'm showing genes X in one tissue and Y in another tissue. And then you're measuring it across postmortem samples of different individuals. They all have these different genetic and environmental factors that they're exposed to, right? And if this gene Y is going up and then the gene X is tracking this gene Y, so this also goes up. And whenever gene Y goes down, gene X also goes down, then you have a statistical correlation among them. And that is the premise under which we operate, that we look for such correlations in the data and then build our network between the different genes in different tissues. But of course, to this community, I do not have to say that correlations are only that, correlations, right? So they don't really reveal any causal effect. And because of various confounding factors, and which is only more so in biology. So there are so many factors that could lead to correlations without any direct relation between the genes X and Y in this particular figure. And so there is multifactorial confounding in the data. So that's one of the challenges that we have to handle. And this data is high dimensional. By that, I mean there is more features than samples. So we have 20,000 genes in, let's say, even 10 tissues, then that's a lot of genes, 200,000 in total, right? 200,000 features in total. But typically, even in the largest of studies, you may have, like, if you're lucky, maybe 1,000 individuals, or typically lesser, 300 or 500, right? And many of these measurements are noisy. And when we get to a particular project, we will also see that different genes are prone to different levels of noise, and that also complicates the questions. So clearly, advances in computational or statistical methods are necessary to make progress in this problem. And our approach at Birch Group is to study a variety of variety of problems in this particular area, where we go from this three-dimensional data that I said, this multimodal data, down to infer something called multi-layer networks, and we call it multi-layer, where each tissue you could correspond to a layer, right? And then there are both interactions within the tissues, which are intra-layer, and then there are interactions across tissues we call interlayer. So we are trying to learn this network representation from this data using the premise that I just described, and handling the challenges that I pointed out. And then and finally, these networks are very huge, so we cannot stare at it and say that this gene is important or the other gene is important. We need graph algorithms to analyze these networks to identify which genes are, for instance, important for tissue-tissue communication. And once we have the predictions, then we can go ahead and validate it. We have experimental collaborators who are happy to or interested in exploring this further. Okay. And so the goal really is start with this three-dimensional matrix that I said. So here we are having one of the dimensions is 3 tissues, and you have individuals and genes, and to use this correlations, and to the extent possible, we can also learn certain causal relations among these genes, and to really understand how these networks are there among healthy individuals, which is what this NIH GTEx data is. But also see how these networks rewire in deceased individuals. And we have some multi-brain region data and certain brain-related diseases where we are interested in studying them. Okay, so this is the higher level picture of it. And then in the rest of the talk, as I said, I want to focus on 2 specific projects. One is causal discovery from noisy data. We said noise is one of the important challenges. And the second project is on multi-layer, some network science measures that are appropriate for multiple layer networks. And the first one is joined with Rahul, Brinda, and Amol. So they are Rahul and Brinda are current members of the group. Amol is an alumni of the group. And we have, I would like to acknowledge the different BERTS group members and IBSC and RBCDSAI members for their valuable feedback and inputs. BERTS meeting we have weekly, IBSC we have bi-weekly among different members of the Systems Biology Initiative, and venue like these for RBCDSAI. Okay. Okay, so let me get to this causal discovery from noisy gene data. So the holy grail is, of course, causal discovery from observational data. So if you're able to do experiments like interventions or perturbations, so here, let's say G and T are 2 genes. If you're a model organism, so like a mouse or a yeast or some other organism, right? I can go ahead and directly alter G. I can bring down the level of G, and then I can test if the T is also brought down. So those are direct interventions or perturbations, but of course in human beings, it's not possible. It's not ethical. And so we have to collect data such as the data that I just described from sets of individuals, and basically work with this observational data where we don't have control over perturbations that we're doing. And so from this, if you don't make any other assumptions, then you're stuck with correlations. A correlation doesn't imply causation. In all the cases, right? So we need what is something called an instrument variable approach, where you can take an additional variable which you know is not downstream of these genes, but it's only in the root of the causal network. In biology, fortunately, we have something genetics, right? So genetic factors, which for most cases, for most diseases, except cancer and other cases where there is DNA mutations which happen, for most diseases and most healthy settings, your genetics is formed at birth and it's not influenced by the level of activity or expression of the genes. So if you see that L and G, L is a genetic factor, let's see, and then G and T are genes. If you see that L and G are correlated, then you can, and if there are no other variables, so under certain other assumptions, you can infer that L controls G and not the other way around. Okay, so that's directly comes from the genetics being fixed at birth. And but the question that we are addressing in this project is, okay, there are existing methods which will deal with this. So this approach is also called a Mendelian randomization, after Mendel, who figured out the genetics, right? So you may remember from your biology classes. So, but what if G and T are noisy to different extents, right? So let's say you don't have a precise measurement of G, but G prime is G plus some Gaussian noise. T prime is T plus some Gaussian noise. So in that particular case, can we develop a method that will both estimate the magnitude of that noise and then correct for it in this gene activity or expression data. And why is it important? So if you take an existing method that works as though there is no error in the data and then apply it to an error prone data where you apply it to L, G prime and T prime, if G prime has lesser errors, like the magnitude of the measurement noise in G prime is less than T prime, then the methods will work fine. Though it will lead to some improper estimates, the structure will still be figured out. But if T prime, if the error in measuring T is less than that in G, then you may even make the worst possible causal mistake that it flips the direction and you may think that T is the one that is causal for G. So which is the worst possible serious causal mistake that we can take. So it's important to handle measurement errors and correct it when we look at causal discovery methods. Okay. And so we take a two-stage framework. So where we use a polynomial regression model to actually predict the measurement error of different genes. And this is this serious error that I was talking about is a problem only when different genes have different levels of measurement error, right? So we need to be able to figure out, given a gene, what the level of measurement error is. And using expensive experiments, we can figure that out. But oftentimes we only have one measurement per individual. You don't have multiple measurements per individual. So we need some ways to predict it. So we do have a model, but that's not the focus of this talk. So let's say we have an estimate of the coefficient of variation. So the measurement error divided by the mean of the gene. So if we have that for every gene, which could be different for different genes, then how do you go about taking certain existing instrument variable based causal discovery approaches and adjusting them for these magnitude of measurement errors that we have inferred? Okay, that really involves two steps. One is adjusting the coefficients of a model. So these are linear regression based models that I'm talking about. We'll get to it in a bit. And then the second step is, once you have these adjusted coefficients in these linear models, how do you actually adjust the statistical hypothesis test that we use to infer the structure? And this falls under a broad category of methods called constraint based causal discovery, as opposed to this other method called score based discovery. So in this constraint-based approach, you do various hypothesis tests. So one is correlation, right? So we have these, let's say we have these three models that we are trying to infer, and we are assuming that there is no other confounding factors. So that's a big assumption. We can get around it in certain ways, but let's get along with it for the purpose of this talk. And so we have a genetic factor L, which is controlling a gene G, which is controlling another gene T. Okay. Or it could be L to T to G, or L, this genetic factor is independently controlling G and T. Okay. And this G and T could be genes in the same tissue or in different tissues, it doesn't matter. Okay. And you have this correlation G and T, which will be true in all these cases, and which is another way to say that using correlation, we cannot infer whether it is causal or an independent model. But if you do conditional independence, where you condition on G and then you see if all the association between L and T is mediated through G. Once you condition on G and remove the effect of G on T or G on L, right, then L and T should become independent. So that should be true in this case. But if you condition on G here, L and T are still associated. So it should not be true in this case, and so on. Similarly, the conditional independence test the other way around. Instead of conditioning on the middle, the G, if you condition on T, then this should not be true. But for this model, if you condition on T, then L and G should be independent, and so on. Okay. And all of this can be realized in various ways. One way to realize it, a very popular way, is using linear regression models. So how do you do that? So again, for this audience who work with much more advanced methods, so the linear regression, this standard estimate of the coefficients, right? So you have X, the set of features, Y is the output, and so you have the standard set of coefficients. For the error-free case, you run basically several linear regression models to perform the statistical hypothesis test in the previous slide. And one such test could be that you are modeling T as a function of G and L is decomposed into L1 and L2. I'm suppressing some details here because L is a genetic factor. It takes three variables, three values, 0, 1, and 2, based on whether you're getting from your father or the mother, which copy of your DNA you're getting from. And so based on that, you decompose it into two dummy variables, L1 and L2. And so you can estimate beta and go ahead. But of course, we are in the case where G and T is hidden and G prime and T prime are observed. And but from the first stage of our work, we have estimated the measurement error, right? So we have the sigma squared EG, which is the error, the magnitude of measurement error in gene G. Okay, so you can show that this particular coefficient matrix can be expressed as this without this minus term, but you just have to simply subtract this term for getting your adjusted coefficients. Okay. And once you have these adjusted coefficients, so this is only one of the tests I'm showing. There are 4 other tests that we have to do something similar. 3 of them are association tests. 1 of them is a conditional independence test, which is actually not a hypothesis test, but more an equivalence test. So we will have to adjust it appropriately. But once you have these adjusted coefficients, then you can derive your adjusted F statistics. That is a standard procedure for figuring out p-values of whether a particular coefficient is 0 or not. Okay. In this particular case, let's take again only one of the 4 tests of causality in a method called CIT. This is called a causal inference test by Joshua Milstein et al., where they work on the error-free case. So we take that and extend it to this error-prone case. And if we have these 2 models, we are essentially asking whether beta 1 is 0 or not. Is T associated with G given L? The null hypothesis is beta 1 is 0. There is no association. Alternate hypothesis is T is associated with G. Okay. And we can, in fact, use the adjusted coefficients from the previous slide that I showed, and then appropriate account of these measurement errors of both G and T and adjust these tests so that we get an error-corrected p-values. Okay. Now we have these error-corrected p-values, and we similarly extend those 3 hypothesis test and 1 equivalence test to handle this. So now we can look at how does this perform on simulated data. On the simulated data, again, we have all of these. L is a 0, 1, 2 variable. So it's a 0 with certain probability, 1 with a different probability, and 2 with a probability that all adds up to 1. And so G and T are Gaussian random variables, and all of these are linear models. Okay, and G prime is G plus some error, and T prime is T plus some error. On the left-hand side is shown some for different sample sizes, 300, 500, and 1,000. And on the right-hand side, similarly, 300, 500, and 1,000. We are showing the power, which is how often we are accurate, right? And then the type 1 error, like what are the false positives, right? So this tells you the true positive rate. On the right-hand side is a false positive rate, okay? So that is what we have. And we can see that our enhanced CIT method, which is shown in the green bars, is much better. On the x-axis is the error of the middle variable G, right? So for certain values of error, as the error in the middle variable G keeps on increasing, that is a problematic case, then T will become wrongly called as the causal variable by existing methods such as CIT. So we can see that as the error in the middle variable increases, we are doing much better without increasing the number of false positives by a proportional amount. This is still being controlled, okay? And we have also verified this in the independent model, okay? And I have not been keeping track of time. So how much time have I used so far?
Sir, about 20 minutes.
Okay. So thank you. Yeah. So this is the project. The first project summary on causal discovery is we have developed a method to estimate and correct for measurement errors during this causal discovery of 2 genes when there is an instrument variable, which is this genetic factor. And we have extended this by using a linear regression based method called CIT. And this addresses a widely prevalent problem in causal discovery. And this is not restricted to biomedical data alone. So you can apply this method to, any sort of causal discovery from observational data. And we have tested it for simulated data, and application to human or yeast gene expression data is ongoing. So yeast, because we have a lot of ground truth causal relations in yeast. So we would like to validate it there. And then to human, because we would like to discover novel relations in that, okay? And so that is the first part in terms of where you go from data to a network model, right? So once you have a network model in all these pairwise interactions, if you put it together, right? So you have a huge network, and it's really a hairball, right? And so if I show that, then you would be wondering, okay, what is up with you? So, we have huge amount of networks. So how do you really distill some new insights? How do you transform those hairballs into insights? So this is a joint project with Tarun and Professor Ravi. So we have, we are trying to pose a problem as the following, where we have again this multi-tissue problem, but this is really, we frame it as a multi-layer problem so that it has wider applicability. Other areas where multi-layer networks could be useful is in fact transportation, right? So you could look at a particular city. In the last talk, you looked at road networks and traffic and road networks, but you could look at the same set of cities served by road networks, by railway networks, by air networks, and so on, right? So those could also be modeled as multi-layer networks. And these multi-tissue networks are one other example. And here for us, with the biomedical focus, our aim is to discover the genes responsible for tissue-tissue communication. We want to discover these genes in the periphery, like this gene G2 here in tissue C, where it interacts not only with those which are inside the tissue, those intra-tissue relations, but also those which are across the tissue, right? So this gene 2, this gene 1, and so on. And we want to, again, come up with network science measures, which specifically centrality, which refers to how central a particular node is to, in terms of the connections to all other nodes in the network, okay? And there are various ways to extend current traditional network science measures that work for a single graph or a single layer graph. All the graphs, the traditional graphs are single layer graphs. And extending it to a multi-layer framework. And so we want to use some design principles, specifically decomposability, which I will refer to later on, to extend existing measures such as those based on PageRank to handle multi-layer networks. Okay. So this is, again, a different representation of what we have seen before. You have this 3D matrix, individual tissues and genes, and you have some way using either the causal discovery method that I showed you, or in this current case, we are just simply using pairwise correlations to infer which of the pairs of genes are correlated in these different tissues, right? And you can, of course, also represent it in this in this larger adjacency matrix, right? Supra adjacency matrix, where each one is, this block is all the connections within layer 1. This block is all the connections within layer 2. This block is all the connections within layer 3. The nodes are exactly the same in all of them. So you have 1, 2, 3, 4, 5, right? So you have 5 cross 5 for each one of them. And then all the cross layer connections, all the interlayer connections are represented in these off diagonal blocks. Okay. And if you use the existing PageRank centrality and apply to this multi-layer network, it is called something called versatility. So they have a fancy name for that. So what it does is you take this network and assume as though that you do not know any layer information. So you just view it as a very big giant network and then run your standard PageRank centrality on it, right? So where the PageRank centrality works by in this iterative procedure where for a node 2, right? For a node 2, it will have high centrality. It has high importance in this network if all its neighbors, in this particular case, we have 1, 4, 6, and 5, all have high centrality, right? And 7, all have high centrality, and so on. Okay, so you look at the centrality of or an importance of a node iteratively or recursively. You define it based on centrality of the neighboring nodes, and that depends on these other neighboring nodes and so on. And that is represented using this iterative equation where x is a vector whose length is the number of nodes in the network. So in this particular case, if there are 5 in layer 1 or 10 in layer 1, 10 in layer 2, it will be a 20 long vector. And then you have x is, A is your adjacency matrix. D inverse is some normalization of the adjacency matrix. So a node like 6 equally divides its centrality among all its neighbors. And then plus this beta 1 is for some conditions to normalize it so that the process converges. Okay, so the iterative process converges. So we have, what we are trying to do is for this multi-layer setting is we do not want to have a single measure for the whole network. We want to be able to harness this information about which nodes and which layers, right? So we have something called a local and a global centrality. We want to decompose the effect of the importance of a node into the effect because of its connections within the layer in which it is present and due to the connections that it has across layers. So those are this A tilde overall matrix is split into this A matrix, which are the diagonal blocks, and the C matrix, which are the cross layer matrix, which are the off diagonal blocks. So we want to be able to decompose the overall versatility or overall centrality into centrality due to local connections and centrality due to global connections. And the way we do it is to simply use these two formulas where the L is an iterative update that only uses the local information in A, and G is an information which uses both the local information A and the cross layer information C in a certain fashion. And again, there are various ways of defining it. And the reason we define it this way is because of this decomposability principle, right? So which I may be running out of time. So, but what I will say is, I can come back to it if you have questions. What I can say is, if you define L and G in the way that I showed before, it's not hard to show that if you add up L and G, then you will have the page rank centrality or versatility if you apply it to the original large giant network. Okay, and then similarly, you can also decompose this global centrality into these layer-specific global centrality. So if there are 3 layers, then you can come up with G1, G2, and G3, and you can decompose G further into what is the effect or the importance of a node with respect to having influence on a particular layer alone. Okay, and these are all biologically motivated questions, and we can further decompose this layer-specific centrality into target set specific centrality. We are interested in a certain set of genes, and we want to know what is the influence of a gene on other sets of genes. And so we want to keep the decomposability principle along every one of these steps. Okay. And in the interest of time, I'm not going to go into the details of that. So, Tarun has, Tarun, the PhD student co-advised by me and Ravi. So he has he has devised this method, applied it to this NIH GTEx data, and also the prior information on interactions called SNAP from a Stanford resource. Okay, and these are some of the preliminary results. So we have also done some simulation results, because you saw simulation results earlier on. So I'm going to just show one result. I know that you may all be eyeing your clock, and your hypothalamus may be kicking in to really get to have your lunch. So I will probably just show this one plot where you are looking at ranking all the genes which are secreted out of pancreas, right? So insulin is a hormone. Any of you who may have certain insulin tests and other things done, right? So we have a lot of diabetes cases. So we have insulin is a hormone produced by pancreas, and then it is a target is muscle or other places where it encourages glucose uptake. So we want to, and there are many genes involved in the production of insulin and the response of insulin. We want to be able to figure out those genes. And what these are showing is that as you look at your top 300 predictions, so these are the amount of, on the y-axis are the number of genes that are recovered by our method. If you rank all of them based on the target set centrality, according to a certain set of target genes that are known to be responding to insulin, we want to know what are the genes that are producing insulin or processing insulin. And this orange is an existing method, and our proposed methods performs, maybe initially it is similar, but later on it performs somewhat better than the existing method, which only looks at degree and not really a careful look at centrality. Okay. And other analyses are ongoing, and I will, in the interest of time, I will go ahead and skip these results and just say that we have in this particular talk, I have hopefully convinced you that there is a need for new computational and statistical methods. There are many more than these 2 projects or these 2 problems that I discussed that are needed to build multi-tissue genomic models in health and disease. And we discussed 2 such methods. One is for causal discovery that estimates. So Brinda was a PhD student mainly involved in the estimation of the measurement R and corrects. So Rahul was involved in the correction of this measurement noise. And then network centrality measures, as developed by Tarun, is important in dissecting this intra versus interlayer effects. Really, the hope is that we go from these methods and from a view of these different organs eventually towards the horizon, to have really whole body genomic models. And currently there are models based on that from on metabolism based models, but not really gene expression or genomic based models. Okay. So I will end here, and thank you for your attention, and I can take any questions.
Thank you for the talk, sir. We have a few questions from Professor Arun Tandirala. The first question: did you consider the error in variables framework for your problem? There is solid PCA-based framework for accommodating measurement errors in EIV regression, which not only estimates the regression coefficients, but also measurement errors simultaneously.
Yeah, so in fact, I was going to refer to it. I mean, it's not a coincidence, or it may be a coincidence that the first talk in this workshop, right, and the first day of the workshop was on error in variables. And then we have something similar to error in variables. So here we have, Yeah. So you could consider this as an error in variables in the sense that we have multiple linear regression models, and then we have estimates of the error, of the magnitude of the error. So we are doing actually these two steps. The one step that I didn't show you, which is we estimate the magnitude of the errors, and then the second step we are extending this linear regression model where we are saying that if you have this particular model, both T and G have errors in them. So in a sense, you can consider this as error in variables, or you can view it as we are not doing any form of PCA, but we are including the or modeling for the error, and then looking at how the statistical test and the coefficients change as a result of the error. So it is in some sense an error in variables approach, yes. But we are going beyond that and applying that to causal inference rather than rather than use it for PCA or other applications. Yes.
So, Mani,
yes, Arun, yeah.
I just wanted to comment on that.
Uh-huh.
So, of course, we have shown in our work that, well, PCA is often thought of as PCA and not as a regression tool. Only very recently we've been highlighting that PCA is extremely powerful and useful in regression, and we have demonstrated that to the effect of causal discovery also. Okay, so that's a great PhD work that one of my students graduated with, and we have shown how you can accommodate both the measurement errors. That is, you don't have to do a two-step procedure, and that's the key. You can simultaneously estimate the error covariance matrix as well as the regression coefficients, and also do causal discovery. All of that in one package. So you don't have to go through a two-step procedure. And I'll just probably take this thing from Mohit. There is one question that I've asked. Your method, yes, is in the EIB framework. I can see that. In fact, at least it is looking at the EIB problem. There is a solution. There are a number of solutions to the EIB problem. Your approach seems to be similar to what is known as a Frisch scheme. So if you go back to the statistical literature, you will come across what is known as the Frisch scheme, which is not new. Actually, it's been there for a long time. And it essentially does what you're talking about, but in a more systematic way. So it accounts for the event errors and adjusts the regression coefficients. It's a two-step procedure. It assumes that you have a knowledge of the measurement error covariances upfront. Like either you have done through experiments or somebody has given it to you. I don't know if you have looked at similarities between these two. I see very strong similarities. But to contrast this with PCA framework, you don't need to perform those expensive experiments to compute the variances. You can actually do a single experiment in which you can get the regression coefficients as well as the error covariances. That's the advantage of a PCA-based framework.
Okay, got it. So if I were to
can I comment, Mani, was one thing?
Yes, go ahead.
The only problem here, Arun, is I think variable versus observation. Here, I think, if I'm not wrong, do you have more variable and less observations, correct, Mani? Or it's not that?
There are more variables, there are more genes and less observations, yes.
Yeah, so that's the issue here.
All the underdetermined problem, you can set up, you can do it in, you can impose constraints to arrive at a unique problem or a unique solution, sorry. But yes, I agree that the problem that we have solved is for the overdetermined case. For the undetermined case, it remains to be seen what has to be done.
Yeah, so let me clarify. I think you bring up good points. So Arun, so let me clarify some of those points. So in terms of using these expensive experiments to figure out the magnitude of a measurement error before we actually test, this two-step process that I was referring to is the one that we have found out for, at least for the biological data where we have a high level of noise. We have some reference studies where we have these expensive experiments which are done. And so we have certain gene features such as gene length and average expression of the gene, which can be used to predict the magnitude of measurement errors. And so in some cases, right, so if you do not have these magnitude of measurement errors beforehand, then it may become a hard problem to identify given just the noisy data, what is the magnitude of the error and what the underlying model is. I understand that you have an approach based on that, but we feel that having this magnitude beforehand based on earlier reference studies and then prediction based on those studies for the current data is more robust than doing it all in a single step. That is why we do it in 2 steps. And the second point is,
so there is an issue also.
If I may complete, 1 second, Arun. Yeah. So the second point is each of these individual steps, as I said, is not new. I mean, the linear regression framework or adjusting it for certain coefficients, but then we put it together in this overall causal discovery framework, in this 2-step framework, and that one has not been done for gene regulatory network discovery. And so that is where the novelty of the work lies. But go ahead, you were saying something.
Yeah. So a couple of quick comments on that. One, with the adjusted approaches, somewhere there has to be a concern that the once you adjust for the regression coefficients and so on, at least in the Frisch scheme, there is this concern, and I'm not sure if it applies to your case as well, but I see very strong similarities. The positive definiteness of the covariance matrices that you have to work with after adjustments is not guaranteed in a Frisch scheme, that there is an issue and it's a very well-known problem. Okay. So I'm not sure if you have looked at or thought about that in the direction, whereas if you were to scale, so even the PCA-based framework, you don't have to actually use a simultaneous thing. I mean, if you know the noise covariance matrices upfront, a better way to deal with this is what the method says: scale the data. Rather than adjust for the coefficients, you scale the data and then you do your linear regression, you'll get very nice results. Okay, where this positive definiteness is not an issue. And the second comment that I have is with regards to causal discovery. I just wanted, it's more of a query, I would say. Is it truly a causal discovery problem, or you have already kind of partitioned and you're just checking the variables into causes and effects, potential causes and effects, and then you're using data to answer further, or you just rely purely on data to partition the variables into causes and effects?
Okay, so there is some extra information you can use in terms of which gene is closer to this genetic marker L, and that is more likely to be a cause. But in this particular scheme, we are not making any such assumptions, because we are going to try out if G is causal for T or T is causal for G, or if it is an independent model. So all of these 3 models are considered as potential models when we test. And of course, there are other assumptions that there is no underlying confounding factor, which I mentioned earlier.
So that's true for all data-driven things. I mean, there is no doubt about that. But one last thing. So I suppose you are looking at static problems. It's not dynamic regression. I mean, there are no lagged relationships and so on.
Yeah, this is static problem.
Dynamic. So there are challenges in causal discovery for static problems. Uniqueness of the answer is a big issue. So I'm not sure if you have thought about that, because when 2 variables, I'm not thinking of genes, I'm thinking of a generic problem. I know generic also has a gene in it, but in a generic sense, when 2 or more variables are instantly related, it is simply not possible to purely discover the causal relationship from data unless you make some prior assumptions.
Yes. I agree with you totally on that. So even in this whole framework where we are trying to build this model on the relation among the different genes, we are not setting out to discover all possible relations, only those relations that are visible in this gene data that we are working with, and also subject to the caveats that you had mentioned, that we won't be able to capture all possible gene pairs. But to the extent that, but there are still many pairs that we discover using this method which may not have been discovered. So that
is this answer unique? Whatever you have discovered, is that an answer unique? Is there some guarantee on that?
Excuse me, sir.
Okay. We will. I will
note. Since we are
down.
running short of time, can we please
sure.
end this conversation offline?
Done.
Yeah. No. I have noted down these, so I can.
We'll take this discussion offline. No.
Offline. Yeah. So on the uniqueness and the Frisch criteria, those are good points. I have noted it down, and I'll get back to you.
Thank you.
Thanks, sir.
Thank you, sir.
Yeah.
As we have come towards the end of the workshop, I invite Dr. Nirav Bhatt to deliver the vote of thanks.
Yeah. Thank you, Mohit. Thank you, everyone. I would like to thank all the presenters who actually made a good presentation and very lively presentation today. And I also would like to thank all the participants who actually participated in the questions and answer sessions. And also would like to thank Mohit, Gokul, Sridhar, and Philji, and other behind the scene actors who actually made it possible. We actually going to organize same kind of workshop maybe sometime at the end of the December or first week of January, where our students will make a presentation regarding their research work. So please visit RBCDSAI page for the next events. And I would like to thank you all of you for spending time on Saturday morning, and have a nice weekend. Looking forward to your participation in the next workshop. Thank you. Thanks, Arun.
Thanks. Yeah, all speakers made a really nice presentation. Really enjoyed it.
Yeah, I also have a suggestion. People, please subscribe to our YouTube channel so that you get updates on all the talks and other things that we post on.
Yeah. Thank you.
Thank you. Thank you for the opportunity.
Thanks, everyone. See you.